Hi, everyone. Welcome to track 2, Quantum Software, Theory and Applications. So I'm Pauline Olitro, and I will moderate the session together with Krista Zufall and Travis Scholten. The three of us are quantum application researchers at IBM Quantum. So I will start with the first 3 speakers of the track, then Krista will present the 2 next speakers, and we will have a short break, and finally Travis will take over. So let's start with the first talk. Our first speaker is Paul Richards, a research fellow at the Nanyang Technological University of Singapore. Thanks a lot, Paul, for being with us today, even though it's very late for you. And so Paul will talk about the impossibility of Landauer's bound for almost every quantum state. Paul, the floor is yours.
Thanks. So I'm excited to share with you guys my recent work with Milei Gu on the impossibility of Landauer's bound for almost every quantum state. This work's been really satisfying because it allows us to revisit and revise our understanding of the relationship between energy and information. In the process, we've gained a deeper understanding of both physics and computation. So the relationship between energy and information, it's been explored for a long time via thermodynamics. So a natural question is, what are the thermodynamic limits of computation? So take a second to think about what would you answer for this. In fact, this was one of the primary questions being addressed at the Physics of Computation Conference 40 years ago. And in working through this question, it played actually a pivotal role in the development of quantum computing. So if you'll let me to paraphrase the conversation that was happening at that time, Landauer had found that heat must be released to the environment for any logically irreversible operation. So Landauer found that heat Q must be larger than the reduction in the entropy of the system. So KT here is the thermal energy of the environment, and delta S is the change in entropy of the system. So this led Charlie Bennett to realize that logically reversible computation is possible and seems to avoid Landauer's heat cost. Ciaffoli and Fredkin agreed. They even had some examples they shared at the conference. This led Paul Benioff to propose quantum mechanics as a physical implementation of reversible computation. And Feynman, of course, agreed and thought quantum computation was a good idea. And the rest is history. Here we are today. But it's important to recognize that even though we usually think of quantum computing as reversible with unitary gates, there still are important non-unitary aspects of quantum computation. So for example, whenever you are initiating a quantum memory register, or you're in a lab, you're trying to prepare a Bell state from whatever the physical system was before, or hopefully when we have error correction, quantum error correction, all of these are examples of non-unitarity, and because of that, incur a Landauer type heat cost. So let's ask again, with 40 years of hindsight, what are the thermodynamic limits of computation? Is it just Landauer's bound? And so many people interpret Landauer's bound as this exchange rate between energy and information, where, okay, I want to reset a bit or qubit. That's going to cost me kT log 2 of energy, of heat. And this is essentially restating the second law of thermodynamics, that entropy production is expected to be non-negative. Entropy production here, I'm denoting by sigma. And when we think about it this way, we know that entropy production is only going to 0 in this quasi-static limit when there's no control restrictions. And so we know that actually limits when Landauer's bound will be achieved. So maybe a better question to ask is, what are the non-equilibrium thermodynamic limits of realistic computation? So here by non-equilibrium, I mean finite time. Realistic, I mean something like constraints on knowledge and control. So Landauer's bound is out. Are there stronger constraints on entropy production? Indeed, and the main result that I am going to be sharing with you today is that no reliable protocol for preparing a quantum state can achieve Landauer's bound for any more than, at best, one of infinitely many possible inputs to the preparation device. In particular, we found that for any reset protocol, for any device, for any preparation device, we have a minimally dissipative state, alpha naught. And for any other input, for any initial state of the system that you're resetting, rho naught, the heat must be larger than Landauer's bound suggests by exactly proportional to the quantum relative entropy between the actual initial state and the minimally dissipative state, alpha naught. And it's useful here to think of the quantum relative entropy as a measure of distinguishability. And also, when we think about some of the mathematical properties of relative entropy, we realize some of the physical implications here. So, for example, when alpha naught, the minimally dissipative state, approaches a pure state, or any state that doesn't have full support, then generic inputs, rho naught, will actually have divergent heat cost. So we see not only an interesting, but actually severe new thermodynamic consequence that I'll be sharing with you today. So let me introduce the framework that we derive this is, it's quite general. So this should be expected often, basically very generally. The main results are derived for general quantum dynamics, where we consider a control parameter x. So the control parameter, it controls the Hamiltonian of the system, as well as the interaction of the system with its environment. And that's from time 0 to tau. So that induces a net unitary time evolution of the system baths supersystem. And the reduced state of the system is, of course, just obtained by the partial trace over the environment. And so now we can think about, we have the dynamics, very general dynamics. How do we get the thermodynamics from the dynamics? Well, in non-equilibrium thermodynamics, the main object of interest is entropy production, sigma. And entropy production is the entropy flow to the environment beyond any reduction in von Neumann entropy of the system. So entropy flow, here denoted as phi, consists of things like heat to the environment divided by the temperature in that part of the environment. And without making any further assumptions, we're able to derive an equality for entropy production. So not just saying that entropy production is non-negative, but actually quantifying exactly what entropy production is for any process. Entropy production is exactly the change in mutual information between the system and the environment, plus the change in relative entropy between the state of the environment and a reference state which would seem to represent the environment in local equilibrium. So interestingly, this doesn't actually imply the second law of thermodynamics. You can have even negative entropy production in general. But if we impose two further restrictions, so in particular, if the system and environment are initially uncorrelated, and if the environment begins in local equilibrium, then indeed we recover the second law, the non-negativity of entropy production. And by the definition of entropy production here, we see that that implies a very general form of Landauer's bound. And this derivation of Landauer's bound is actually really helpful for seeing that any quantification of entropy production, any non-negative quantification of entropy production, gives a sharper bound than Landauer's. So let's consider now the thermodynamics of any quantum operation that we want to perform on our system. The system will have initial state rho naught, and we want to perform a quantum operation gamma. So an implementation of gamma will be if we fix the initial state of the environment and fix the control protocol. And we can ask for a fixed implementation, how does dissipation depend on the initial state of the system? So I've introduced the subscript rho naught here to emphasize the initial state dependence. And we find that in all cases, the entropy production beyond the minimally dissipative, the minimal dissipation is exactly proportional to the reduction or the contraction in relative entropy between the actual input to the device, rho naught, and the minimally dissipative state alpha. And again, thinking of relative entropy as a measure of distinguishability, this says that we have dissipation from a loss of distinguishability of these quantum states. So the implications are profound. Most immediately, we see that non-unitary operations cannot be thermodynamically optimized for all initial states simultaneously. So recall, this is things like initiating a qubit register, creating a Bell state in the lab, quantum error correction. All of these non-unitary operations that incur a Landauer's cost cannot actually achieve Landauer's bound unless we utilize accurate knowledge of the inputs to the device. So it's interesting to compare this to the classical result obtained by Kolchinsky and Wolpert in terms of the Kullback-Leibler divergence. And we see that the quantum correction is exactly the change in coherence on the minimally dissipative basis, eigenbasis. And there's immediate implications for the thermodynamics of computing and quantum computing, which we're especially interested in today. So there's a thermodynamic penalty for modular circuit architectures. And with the rest of the time that I have today, I'm going to talk about quantum state preparation. So we want to think about any reliable reset protocol. The goal is to reset any initial state to a desired state, R tau. And we'll say that a protocol is reliable if it takes the actual final state within epsilon distance of the desired final state. So as you might anticipate, the distinguishability of final states goes to 0 as you reliably reset. And so that simplifies actually our general equality to this nice result here, saying that the extra dissipation from any non-minimally dissipative input is just exactly the initial distinguishability between the initial state rho naught and the minimally dissipative state alpha. And then, as promised, we can recover this heat bound when we suppose that the environment just consists of a single thermal reservoir at temperature T, and also we suppose the second law of thermodynamics. So now we have this nice, you might even say cute, theoretical result. But there's kind of a question of practicality of, well, what's it good for? What can we do with it? And in particular, at this point, it might seem like alpha is some pretty abstract thing. It's some density matrix on some vast Hilbert space. Well, fortunately, we've found what the minimally dissipative state alpha is analytically. So how do we do that? Well, we've done this by recognizing that entropy flow is an affine function of the initial state. So we introduce the entropy flow vector, phi vector here. And A here is the block vector of the input state. So if we know the entropy flow from the completely mixed state, and here I'm talking specifically about the example of qubit reset. So entropy flow from the completely mixed state and this entropy flow vector, then we would know entropy flow from any state. So we can actually obtain these two objects via simple linear algebra when we have access to whatever four experimentally accessible states you have. So let's say in the lab, you have access to X, Y, Z, and minus Z states. Okay, whatever initial states you have access to, you run those through your preparation device, and you look at the entropy flow. From these, there's simple linear algebra to get you these two objects. And from those, we find analytically that the block vector for the minimally dissipative state is the simple function of the entropy flow vector. So finally, let me give you an example that gives strong validation of our result in this case of Lindbladian dynamics. So here I'm going to allow us to control the energy gap for the system and also the orientation of the energy eigenbasis. And we want to reliably reset to the 0 state. So here you'll see there's an example of reliable reset. On the left, you'll see 10 random initial conditions. The top 3 panels are the time evolution of the block vectors, the components of the block vectors. And the bottom 3 panels are the evolution of thermodynamic quantities. And this example reset protocol was just kind of a sigmoidal increase of the energy between the levels, slowly increasing it, and some rotation of the energy eigenstate orientation. And we can see that whatever initial condition is reliably being taken to the 0 state. On the right-hand side, you'll see 1,000 initial conditions being plotted. The red circles along the diagonal are strongly verifying our theoretical predictions. This is dissipation against the relative entropy. And the blue crosses are showing the role of coherence in determining dissipation. So here you'll see in the block sphere, so the star here is representing the block vector for the minimally dissipative input. And you can see that the minimally dissipative input can be coherent in the energy eigenbasis. And we also see that any coherence relative to that state definitely leads to dissipation. Finally, the same dynamics, but a different implementation of reliable reset. Here, in this example, we just have basically relaxation dynamics. So you start with just a very high energy of one of the states, and so the system will just relax to the low energy state. And in this example, we see that the minimally dissipative input is close to a pure state. And because of this, you can see that the dissipation from typical from generic inputs is many times Landauer's bound. And we also see that when dissipation is so large that the classical result basically dominates, it basically explains almost everything because the contribution from coherence is limited by the dimensionality of the quantum system. So there's at least 2 reasons to really care about minimizing entropy production. The first is just energy efficiency. We want to avoid draining our computer's battery or our quantum computer's battery. The second is maybe even more important for getting quantum computing off the ground in the first place. And it's the fact that heat threatens decoherence in a very delicate process. So we should pay close attention to the lessons learned. And to remind you, the main results here are that non-unitary operations cannot be simultaneously thermodynamically optimal for all inputs. This suggests tailoring the device for the expected input. At the same time, there's a thermodynamic penalty for misaligned expectations. And we've seen that dissipation diverges as the minimally dissipative state approaches a pure state. So if the inputs are kind of unknown, uncertainty, then maybe the best thing to do is to optimize the device for the fully mixed state. Finally, I'd like to point you to some relevant references for this conference on the thermodynamics of computing. I'd like to thank my collaborators and thank you for listening. I look forward to any discussion and welcome any questions you have.
Thanks a lot, Paul, for this very nice talk.
Thank you.
We have maybe 1 minute left for questions, but I would like to encourage everyone to post your questions in the Q&A box, and we will try to answer them now. If not, we will make sure that you get an answer by email. So I see 2 questions. One is, okay, wouldn't the easiest state to reset just be the already reset state?
It's an interesting question. So actually not typically, maybe, okay, easy in a way, easy to implement, but bad thermodynamically. So the last example I showed here basically does that. It says that the minimally dissipative state is basically the zero state you want to get to. And this is just kind of the stupid protocol of basically make that, hold the Hamiltonian fixed and make that the Gibbs state, basically. And in this case, you actually do terribly. So it's easy to do that. So if you want to reset, if you want to do quantum computing, usually you need some pure states. You need some zeros or whatever. So in that case, thermodynamically, it's not a good idea. We see that when we design our device to be optimal for something close to a fully mixed state, then the dissipation is actually going to be on the order, at least, of Landauer's bound. And the more you know about what the inputs will be, the better you can do.
Okay, thanks. There's another question. What will happen if you have higher spins, such as spin 1 dynamics?
Yeah, so if we have basically larger quantum systems, then in terms of solving for the minimally dissipative state, it's basically the same idea. This part kind of goes through slightly adjusted, but the main things that we've derived, so qubit reset was kind of an example, but first we have examples for any quantum operation whatsoever, and secondly, we have the more specific results about reset, so it applies to that as well.
Okay, and let's take one last question shortly. So is there a way to keep the units separate?
I'm not sure what you mean by units.
So I think we can maybe send you this question later and
okay.
In the sake of time, move on to the next speaker now.
Okay, great. Thank you.
Thanks a lot again. So our next speaker is Yui Kwek, PhD candidate from Stanford University. And she will talk about how to learn a quantum state, also known as private learning implies quantum stability. So Yui, the floor is yours.
Hello, I'm just going to start the screen share. Okay, hi everyone. My name is Yihui. I'm a PhD candidate at Stanford University. And today I'll be talking about a project that I recently completed entitled Private Learning Implies Quantum Stability. But what we really do is show some surprising connections between different ways of learning a quantum state. And I'll clarify what that means shortly. So this is our archive paper, and this was done with my wonderful collaborators from IBM, Srinivasan Arunachalam and John Smolin. So just to back up and give some motivation for the idea of learning quantum states, this is kind of a computer science notion that has physical origins in the idea of this task called quantum state tomography, which is a fundamental task in any quantum experiment. So what this task is that given a physical system, or given a way to prepare a physical system in an unknown quantum state row, one is to estimate the density matrix rho. And so this is pictorially illustrated below. You start off with many copies of the unknown state rho. You're allowed to do measurements on rho, which are modeled as POVMs. Each measurement produces a real valued outcome, and then by collecting the statistics of the measurement outcomes and then putting them into a processing algorithm, the processing algorithm then outputs a classical estimate rho hat of what rho actually was. So this is how quantum state tomography generally goes. And the problem with this is that you generally need many measurements, which means that you need to prepare many copies of the unknown state before you before you can gather enough data for your processing algorithm to give you a good estimate rho hat. And to be a bit more rigorous about this, the observation here is that full quantum state tomography consumes lots of samples. So when I say samples, I mean state preparations. And the emphasis here is again on the word full, because in the task that I outlined just now, what you want to do is output an estimate of the entire density matrix. But of course, the whole reason for this presentation today is that sometimes you don't need to output an estimate of the full density matrix. You can estimate just part of the density matrix or the relevant parts of the density matrix, and that also works. To be more quantitative about what I just described, given copies of an unknown d-dimensional quantum state rho, we want to get an approximation of the full density matrix rho. And these papers outlined here have shown that the number of copies of the state you need to prepare is on the order of d squared. And this is really bad because, as we all know, for a state of n qubits, the dimension of the Hilbert space is exponential in n. So it means that, in general, you need exponential in n number of copies of the quantum state in order to do full quantum state tomography. So Scott Aronson asked a while back if there are other ways to learn quantum states that perhaps don't consume quite so many samples. And so the core idea here, just in a very general fashion, is that instead of learning the state fully, one could consider just learning its essential properties. And typically, the underlying statement, essential properties, refers to the probability of the state accepting on a two-outcome measurement. And this is really a beautiful field because it's kind of at the intersection of computational learning theory, which is the sort of theory that has been developed to kind of explain neural networks, as well as quantum mechanics. So it's kind of like applying this beautiful theory to the problem of learning quantum states or learning quantum gates or like various things in quantum mechanics. But today we'll just be concerned with learning quantum states. So Scott also introduced a bunch of quantum state learning models, which basically vary in the ways that the learner is allowed to like probe the state. But so I'll explain all of those shortly. But the point here is that in all of these reduced learning models where you don't want to learn a full state necessarily, but just learn some properties of the state, it's often a dramatically easier task than learning the entire state. And it can actually cut down the sample complexity from exponential to linear in n. And so what this presentation is about is that many of these essential learning models are deeply connected. And by deeply, I mean like information theoretically. So we can connect the complexities of each of the learning tasks. Okay, so now I'm going to define what it means by quantum learning. So the critical observation here is that every state rho defines a function. Of course, it defines many possible functions, but we're interested in this particular function, which is f rho, which is basically the probability of a two-outcome measurement outputting accept when that measurement is applied to the quantum state. So the domain of this function is that of all two-outcome measurements. The function is characterized, it has an implicit argument, which is rho. And then the range of this function is a real number between 0 and 1. And that has an interpretation as the probability of the measurement accepting on the state rho. So if we consider many possible options for the state that we actually want to learn, say we know that the state comes from a particular set, then every such state defines a function f rho, and varying over all the possible states, we actually get a whole set of functions, f rho. So the idea is that we call this the function class, and the whole point of computational learning theory is to tell you how easy it is to learn a function class. But in this case, we have chosen a function class to be the set of f rows, where rho is allowed to vary. So the meaning of quantum learning is that you have the following task. You want to learn how to predict the trace of some new unseen measurement acting on rho to epsilon error. And so in some variants of this task, you are given examples which take the form, each example takes the form of measurement and then some approximation of the acceptance probability of that measure. That's the trace EI rho with a tilde approximation. And so I'm going to now go through a bunch of quantum learning models. And it's going to be quite quick, unfortunately, because there are quite a few to go through. But we're just going to focus right now on two. So the first is packed learning. So in packed learning, the learner receives all these examples at once, and then the learner is going to run their learning algorithm. And at the end of it, the learner is supposed to have a learning algorithm that is able to predict trace E nu rho with high probability over the choice of E nu. So that was packed learning, and packed actually stands for probably approximately correct. But the other main learning model that we're going to focus on is called online learning. And the main difference between online learning and packed learning is that is the nature of how the learner receives the examples. So in packed learning, all the examples are received at once. And those of you who know machine learning can think of it as the learner getting all the examples in a training phase, and then there'll be a test phase after that, during which the learner is supposed to do really well. But for online learning, there is no division into a training phase and a test phase. Rather, what happens is that the learner receives the examples one by one, and after the learner sees every example, it has to predict trace EI rho. So when I say the learner sees an example, it means that the learner actually receives EI. So that's like a question, and then the learner has to answer with its prediction of trace EI rho. And then the learner is given a correction, which is whether it was correct or wrong and what the actual value is. And in this way, in this sequential manner of receiving examples, the learner uses the correction to refine its prediction algorithm along the way. And so there's one important thing that I have to mention, which is that in the version of online learning that we're considering, the goal is for the learner to make as few prediction mistakes as possible before it reaches a point when its prediction algorithm is so good that it's always going to predict correctly. So in online learning, we're concerned with the number of mistakes, and that's the complexity of online learning. So I'm also going to talk briefly about two other learning models. And the first is called shadow tomography. And basically in shadow tomography, it's a very similar setup where you have M values of, you have M measurements E, and you have a class of quantum states, and you have an unknown quantum state that's from that class of quantum states. And then you're supposed to be able to predict trace EI rho for any of the EIs from your bag of measurements. And the very last model I'm going to talk about is learning by communicating the state. And again, this is a learning model that doesn't actually use examples. So what happens is that you can think of it as an interaction between an Alice and a Bob, where Alice knows the rho and Bob knows the E, and they only share a classical channel. So the goal for both of them is for Bob to be able to output trace E of rho, but because the information is kind of delocalized, so each of them has one of the two arguments. So Alice is supposed to kind of communicate the rho to Bob over the classical channel. And then the goal is to minimize the number of classical bits that Alice has to send to Bob before Bob can output trace E rho. or a good approximation of trace E-row. So our contribution is to show how all these learning models are connected and also connect them with combinatorial parameters. So what's a combinatorial parameter? Well, a combinatorial parameter is given a function class, it kind of measures how complex the function class is. And I unfortunately won't have time to show any examples, but some of you may know the VC dimension or the little stone dimension, and these are examples of combinatorial parameters. But the particular parameters that we're interested in today, or there is one particular parameter we're interested in today, which is the sequential fat shattering dimension. And this is basically what I have in orange in the diagram, well, one of the two boxes in orange. And this is basically a combinatorial parameter of a class, which kind of measures how difficult the class is to learn in an online fashion. So it's kind of like a proxy for just counting the number of functions in a class. It actually counts the number of functions in like a clever way. Just to kind of underscore the connection between sequential fat shattering dimension and online learning, there's an operational interpretation of this combinatorial parameters, which we're going to call SFAT, which is that it upper bounds the maximum number of prediction mistakes that a learner can make in online learning. So recall that in online learning, the learner receives the example sequentially, and then after every example, the learner is supposed to immediately output a prediction. And if the learner makes a mistake, that's bad, and we want to minimize the number of mistakes that the learner makes. And so the number of mistakes required for the learner to learn a function from a function class is at most the sequential fat shattering dimension of that function class. And again, I apologize for not being able to actually define that dimension, but you can just think of it as being similar to the VC dimension. Okay, so this was known classically in the sense that it was known for kind of learning real valued functions, but without the kind of feedback that you would get from learning quantum states. But we proved an analogous theorem for the problem of online learning quantum states. And so that's there. So we showed that if your online learner wants to learn the class of functions defined by quantum states, then the number of mistakes made by that learner is also upper bounded by the sequential fat shattering dimension of the class of quantum states. So that's one of the implications that we showed. The other two, or the other two chains of implications there were also known classically in the sense that they were proven for the problem of classically learning a function class consisting of Boolean functions, so functions mapping to 0, 1. But of course, for quantum learning, we don't want to learn Boolean functions. Instead, every quantum state corresponds to a real valued function, and so we want to learn real valued functions. And another pertinent aspect of the quantum learning problem is that typically the examples come from some physical measurement, and so unlike in the Boolean function learning case, the examples tend to be noisy. So you can only get an approximation of the true acceptance probability. And so we basically reproved all of these implications for the problem of learning real valued functions with noisy examples. So the box means that the set of implications was quantized, but I just want to focus your attention on the chain, on the very last chain at the bottom left-hand corner of the screen. So so before I box that up, what the last chain says is that if one is able to online learn a Boolean function, then one is also able to learn it in a PEC manner, but not only PEC, it's also in a differentially private manner. That's what the letters DP stand for. So differential privacy is kind of a very intriguing algorithmic notion that says that basically regarding the randomized, so if you have a learner, which is a randomized algorithm, a differentially private learner is one where if you give it two sets of examples that only differ in a single example, then you want the performance of the learner to be very similar across the two sets of examples, or you want the probability distribution of that the learner outputs to be very similar if you just tweak the input by a tiny thing. So that's what differential privacy means, but that's not really the focus. But anyway, the point is that if you have an online learner for a particular function class, the very last chain of equivalences tells you that you can also create a differentially private packed learner for that function class. And so what's kind of nice about this was that if you kind of put all three chains of reasoning together, it starts and ends at kind of differentially private packed learning. Although, indeed, there's a small asterisk there, which is that it starts at pure differential private packed learning and ends at approximate differentially private packed learning. And so, of course, it was of interest to know to us to know whether all these implications also go over to the quantum setting. But actually, they don't necessarily. So we managed to quantize this first implication here, which is that if you have an online learner for a function class, then you can also learn the function class in what's called a stable manner, which is kind of another algorithmic concept. But the problem was that actually this link from learning the function class in a stable manner to learning it in a DP-packed manner is not quantizable. And so we showed a no-go theorem for this link. And the reason it's not quantizable is because classically this link was shown for learning a discrete set of functions, but once you go to the continuous regime, it's like no longer possible. And we have to go to the continuous regime because we're interested in learning quantum states which correspond to real valued functions. Okay, so just putting everything together, we have all the implications that we showed just now, but we also have a no-go theorem going from stability to approximate DP pack. And this classically also makes a contribution because many of these implications were not known for the problem of learning real valued functions. But now we know that some, like almost all of them, go through. And another new thing that we added was that we connected all these models of learning quantum states to a new model of learning quantum states, which was not considered classically because it doesn't really make sense classically, which is called shadow tomography. And to be more specific, it's a gentle version of shadow tomography, which also, and the word gentle actually also has links to another notion of differential privacy. And basically what we can get from kind of using this sequential fat shadowing dimension to characterize the complexity of all these learning models is that we actually sped up the sample complexity of shadow tomography when the class of states to be learned is kind of a subset of the full set of n qubit states. So if you have some prior knowledge about your state, then the fact that we can now characterize shadow tomography, or the fact that we can now characterize online learning of quantum states by this sequential fat shadowing dimension also therefore implies that shadow tomography is faster than was originally thought. Okay, so just to conclude, we've shown implications between many reduced models of quantum learning, and this is good because it enables us to port algorithms from one model of quantum learning to another. And as part of our work, we also introduced the notion of stability of a learner for quantum states. And we also made a classical contribution, which is showing that many of these implications also hold for learning classical functions. So a most interesting future direction would be which algorithms can we now port from one model to another if we know that these models are kind of information theoretically related. And so thank you all for your attention. That's the end of my presentation.
Thanks a lot. Thanks a lot, Yuri, for this nice talk. We have time for just one question, and that would be, is there an analogy between online learning of a quantum state and what is known as reinforcement learning in machine learning?
I believe that there isn't. So I think what online learning is, okay, so online learning is kind of like a theoretical model that models a learner that receives the examples one by one. And I think that the practical kind of like interpretation of online learning is standards. So it's not really the same as reinforcement learning. Yeah.
Okay, thanks a lot. Thanks a lot, Yuri, once again. Unfortunately, we have to move already to our next speaker. And our next speaker is Davide Ferrari, a PhD student at the University of Parma. And he will talk about compiler design for distributed quantum computing. So Davide, if you would like to take over, the floor is yours.
Thank you, Pauline. Hello, everyone. So I will talk about compiler design for distributed quantum computing. And this talk is based on a recently published work, and you can find the reference at the bottom of the slide. I will first start with an introduction to compilers for distributed quantum computing, and then I will focus on compiling in the worst case scenario. This is a joint work between the University of Parma and the University of Naples, and here you can see the project team and the references to our research groups and activities. Now, the growing demand for large-scale quantum computers is motivating research on distributed quantum computing architectures. And we have this vision of a quantum internet where remote quantum processing units can communicate and cooperate to execute computational tasks that a single device cannot handle by itself. As many of you may know, when we want to execute a circuit on a device, we first have to compile it, which means that we have to translate it into the most efficient equivalent of itself, while taking into account the characteristics of the device that will actually execute the computation. And usually, compilation strategies are composed by sequential passes that perform placement, routing, and various optimization tasks. So, for example, if we want to execute the circuit on the left on a device with a coupling map such as the one in the middle, we could do that by choosing a good initial mapping between the virtual qubits of the circuit and the physical qubits of the device, which is depicted in blue, and by inserting some swap gates. If we switch from compilation over a single device to compiling over a DQC architecture, then it's clear that we need a new generation of quantum compilers to map any quantum algorithm or quantum circuit to any DQC architectures. And while doing so, there are several challenges that arise. Clearly, a key requirement for distributed quantum computing is the ability to perform remote operations. So let's take, for example, the quantum processor. Then we can devote a subset of qubits at each processor as communication qubits, and then exploit entanglement, namely Bell states shared between those communication qubits, to perform remote operations. For example, we can use a simple circuit that just requires local operations and a classical channel to send measurement outcomes in order to achieve a remote synod. But such operation will consume the Bell state, and then we will need to generate and distribute a new Bell state. And although it's unlikely that a data qubit could be dynamically turned into a communication qubit, given the dedicated hardware such as matter-flying qubit interface, it's plausible that we could use communication qubits for computing. So a distributed quantum compiler could reserve a subset of the communication qubits for computing. Another feature of the QC architecture is what we call dynamic connectivity. So we can visualize a quantum link between two QPUs as a set of links between the data qubits across the QPUs. And this set of links will be subject to simultaneity limitation, which means that the number of remote operations that we can execute in parallel on those links is bounded by the number of quantum links available in parallel between the QPUs. So in this case, if we have just one quantum link, we can only execute one remote operation at a time, which which means that all the other links in the set that are not interested by such a remote operation will not be available. And there's also what we call consecutiveness limitation, because before we can execute another remote operation on the same quantum link, we have to wait until a new best state has been generated and distributed, which will most likely take a lot more time than executing local operations. So we want to minimize the number of remote operations rather than the number of local ones in the compiled circuit. Now, if we switch to a more complex architecture, we can see that by exploiting entanglement swapping, we can increase the connectivity between QPUs, creating a sort of virtual quantum link between QPUs that did not share initially a best state. And this is done by a simple application of quantum teleportation at the cost of consuming best states at the intermediate QPUs. So we need to find a trade-off between the augmented connectivity that we want to achieve and how many EPR pairs or best states we are willing to consume and that we will eventually have to regenerate for other remote operations. So now that I have talked about some of the main challenges and dynamics that arise when compiling on a QC architecture, I want to focus on the worst case scenario and how well we can perform when compiling in such a case. So let me envision the QC architecture where we only have one data qubit available at each QPU, and QPUs are interconnected through a one-dimensional nearest neighbor topology with just one quantum link between neighboring QPUs. And it is clear that with such an architecture, the overhead induced by any real-world architecture will be upper bounded by the communication overhead induced by this worst-case one. Given a quantum circuit that we want to compile on n qubits, there can be at most half of n CNOTs in each layer, and given the worst-case architecture, all of these CNOTs will be remote CNOTs. Moreover, if all of the CNOTs in an arbitrary layer overlap, like in layer I+1 in this circuit, and we have a trivial mapping between qubits in the circuit and QPUs, so that qubit 0 is on QPU 0, qubit 1 on QPU 1, and so on, then all of the CNOTs will be between non-neighboring, non-connected QPUs. And this is clearly the worst-case scenario. And to tackle this problem, we envisioned two basic strategies. The first one is just to exploit entanglement swapping whenever needed, and the depth overhead of using such a strategy for the compilation of an arbitrary layer does not exceed half of n multiplied by a constant factor, which depends on the underlying hardware architecture and is given by the cost of performing link entanglement, which means generating and distributing best states, the cost of performing entanglement swapping or best state measurements, and the cost of performing a remote CNOT. The second strategy, we called it data qubit swapping, and the rationale between this strategy is that whenever the original quantum circuit presents repetitions of the same CNOT interaction pattern between qubits, then moving the data qubit states could provide better performance. So we want to arrange the data qubit states within the QPUs, and this can be modeled as an array sorting problem. Specifically, in such an array sorting problem, there can be two disjoint cases. The first one is that there exists a CNOT acting within the first, which means that there exists at least one CNOT acting on the last half of n qubits. And in this example, we can see we have a remote CNOT between Qi and Qj, depicted in red, in the first half qubits between non-connected or non-neighboring QPUs, and another remote CNOT between Qk and Ql. And we can satisfy the requirements to execute such CNOTs by performing two remote swaps in parallel, so that now the qubits interested by the states of the qubits interested by the CNOTs are on neighboring QPUs. The second case is where each CNOT acts on two qubits belonging to both the half portions, And again, we can perform 2 remote swaps in parallel to then being able to execute the remote synods. So we can see that at each iteration of this sorting routine, we are satisfying the requirements to execute 2 of the half of n synods in an arbitrary layer. And this means that the depth overhead of this strategy for an arbitrary layer does not exceed n divided by 4 multiplied by dqs plus d prime qs, and both the dqs and the prime qs are again constant factor depending on the underlying architecture. So if we assume, for example, that to execute a swap we need to perform 3 consecutive synods, then dqs, which is the cost of a remote swap, is then 3 times the cost of link entanglement plus entanglement swapping for a remote swap between non-neighboring QPUs plus the cost of the remote synod, while the prime is the cost of performing all of the synods in the arbitrary layer after the sorting phase is done and all the qubits are on neighboring QPUs. To assess the performance of these 2 strategies, we implemented a compiler that takes as input a quantum circuit in an open pass format, produces the distributed version of the quantum circuit, and has a computational complexity equal to big O of d n squared, where d is the depth of the input circuit, and n is the number of qubits in the circuit, which of course translates into the number of QPUs in the worst case, for the worst case architecture. Now, just a side note about the sorting strategy or data qubit swapping strategy. We implemented it as a Nyberg strategy, where data qubit swapping can be applied to a subset of qubits. So, for example, with this circuit, we will apply entanglement swapping to enable the execution of the first synod, and then data qubit swapping to enable the execution of the last 2 synods. We compared our compiler with the one proposed by Anders Martinez, which is characterized by no limitation over a number of communication qubits per QPU, and assumed an hypercube topology. So just to be clear about the differences between the assumptions made, in the worst case scenario, which is the one on which we compile, a blue edge represents just 1 quantum link or 1 APR pair shared between neighboring QPUs, while in the hypercube topology, which is a highly connected topology, a red edge could represent more than 1 quantum link between connected QPUs. These are the results regarding the data qubit swapping-based strategy. On the x-axis, we have the Martinez, the results from Martinez compiler. On the y-axis, the results from our compiler. Depicted in red, we have the depth of the compiled circuits, where we can see that we are pretty much on par with the Martinez compiler, and sometimes we are even a lot better. If we focus on the blue plot, where we have depicted the number of link entanglement generation layers, which are the time slots in the compiled circuit, distributed compiled circuit, dedicated to generation and distribution of Bell states, we can see that we are in general a bit better than Martinez, and we are inevitably worse in terms of APR pairs consumed, which is plotted in the last figure, and this is due to the hypercube topology, which is a highly connected topology, where if we want to perform, for example, an entanglement swapping or a remote swap between any pair of qubits, any pair of QPUs, we need at most log of n APR pairs, while with the worst case architecture, we could need up to n pairs. We also validated the theoretical upper bounds that I showed before, and we saw that for every circuit tested, we can respect those upper bounds by a very good margin. Now, I would like to conclude with just a couple of thoughts on future work. So, of course, with the different network topology with respect to the worst case one, new optimization challenges arise. So, for example, if we have more than one data qubit available at each QPU, then of course only a subset of the synods must be mapped into remote operations. And so we need to find a good mapping between the qubits in the circuit and the qubits in the QPUs in order to minimize these remote operations. So next iterations of DQC compilers should support any practical DQC architecture and pure coupling map without making any assumption about the topology. And we should also study strategies for noise-adaptive compilation of quantum algorithms to DQC architectures, which is something that has already been done and is still being done for compilation over single devices. And of course, all of the above, and probably even more, should be supported by the definition of a DQC-oriented enhancement of OpenQuasm or any other kind of level description language for a distributed quantum circuit. Here are just a couple of references. The first one to the work on which this talk was based, published recently, and the one by Pablo Andres Martinez and Chris Yunen about distribution of quantum circuit via hypergraph partitioning. This is the end, and I thank you for your attention. There's still probably time for a couple of questions.
Thanks a lot, Davide. So, yes, we have time for questions. I do not see questions in the chat right now, but don't hesitate to send questions even later, and we will transmit them by email. So maybe I can just ask a question. How do you select the test cases for benchmarking your algorithm?
Yes, I used a very famous test set, which was used originally for the first IBM challenge about compilation, and has then been used practically by every research group that does compilation over single devices. And it's a very heterogeneous set of circuits. Okay,
thanks. I actually see a question now. So how does topology factor in here? How does the topology factor enter in here? I suggest that the person who has the question maybe rephrases or gives us more detail.
Yes.
And we will transmit you the questions. Okay, so I see no further questions. So thanks again, Davide.
Thank you, Pauline.
And now Krista will take over and introduce the next speakers. Thanks a lot, everyone.
Thanks a lot, Pauline. Hi, my name is Krista Tofa, and we can jump right into the next talk, who is actually given by Professor Vladimir Korybin and Kun Zhang from the Stony Brook University, and they'll be talking about hardware-efficient search on IBM quantum systems and non-abelian quantums, and how non-abelian quantum search reduces noise factors. So please take it away.
Hello. You see my screen, right?
Yes, we do.
So thank you very much for inviting me. It's a privilege. So we reformulated quantum search so it's become less vulnerable to noise. So first of all, everybody knows Grover algorithm, but still I want to remind it because everybody use their own notations and their own point of view. So the Grover search based on the one-way function. We have this function which is easy to evaluate the function, but the inverse function is exponentially slow to calculate. The everyday example is telephone directory. So for the simplest case of Grover, there is only one target item. People also call it marked item or solution. That's one item in the database which we're supposed to find. Grover algorithm starts with this S state, which can be obtained by applying Hadamard to each qubit, which was set up to 0. So this is fully diagonal state. It's equal superposition of all basis vector, and each basis vector corresponds to an item in the database. So Grover algorithm has two main operations. One is query to the oracle, which is identical operator -2, and this is projection to this target item, the one which we're supposed to find. This query to the oracle, also called a phase kickback in the literature.
Vladimir, I'm sorry to interrupt you, but should you share your screen? Are you talking to some slides here? You are not sharing your screen, so we hear you talk, but we don't see the slides.
Entire screen, allow. Do you see my screen now?
No.
Yes, now we see your screen.
Okay, shall I go to the beginning? Shall I start again?
I think it would be worth it, yes, because you were speaking, but nobody could see what you were talking to.
All right. So I apologize for this. And then we reformulated quantum search, so it becomes less vulnerable to noise. So first of all, a reminder of the Grover search. Everybody knows Grover, but everybody used a little bit different notations. So let me remind Grover. So it is based on one-wave functions by f, and then it is polynomially fast to calculate, but inverse function is exponentially slow. In the simplest version of Grover algorithm, there is only one target item, the one which we're supposed to find. And then that's an actual subroutine of Grover algorithm. We start with state S, which is complete diagonal, which is sum with the equal coefficient of all basis vectors, and each basis vector corresponds to an item in the database. And there is two linear operators. One is called query to the oracle. Also in the literature, it's called the phase kickback, which is identity minus 2 multiplied by projector on this target item, marked item, as a solution. That's one which is supposed to find. And there's also a diffusion operator, which is a reflection in this S, which we already know how to build by applying Hadamard operator to 0000 state. Diffusion operator, it's a reflection in the average of all items in the database. This reflection operator, by the way, will be modified in our approach. This is a standard kind of, we call it global or normal Grover, but we're going to modify this. And so normal, usual Grover iteration is a sequential application of the oracle and diffusion or phase kickback. And then, of course, after I apply this much iteration, which is pi squared of n divided by 4, integer part, then and measure, then I will find the target item with probability close to 1. Well, maybe a little bit less than 1, 1 minus 1 divided by n, and total number of entries into the database. So Grover algorithm is strictly optimal in the complexity measure, which is number of queries to the oracle. Oracular measure is absolutely the best. It was proved by Zalka in 1999, cannot be improved. On the other hand, we argue that this is not a practical measure of complexity. So we argue that other measures for complexity should be used, because diffusion operator also expensive. It's done by means of n-Toffoli gates, which we have to write down as a sequence of 2-qubit gates, which produce a lot of noise. And then I mean, this also should be taken into account. So we argue that depth is better measure of complexity. So from the point of view of depth, Grover can be improved. The depth of Grover, we can modify Grover, make it a non-abelian version of Grover, reduce depth, and this will reduce the influence of noise. Now we start our version, our modification of Grover. So we subdivide database into blocks, this many blocks, 2 raised to the power n minus m blocks. And then basically we run Grover in each block simultaneously. So this means that we use different diffusion operator, which we call local, d sub n. It was different from the original Grover, because here we make this reflection into the average inside of each and every block. So it's different. So local Grover operator is same query to the oracle. Nothing happened to the query to the oracle, but diffusion operator is different. But we still have the previous Grover diffusion operator, which we denote G sub n, and local and global, they don't commute. Actually, we can write them down as matrices 3 by 3, so elements of O3 group, and they don't commute with one another. This is, we shall discuss what's the significance of this later. Also, right now, we run our algorithm on the small quantum computers, but eventually, hopefully, we shall run it on the larger quantum computers with more qubits, and then at different steps, while search algorithm is running, we will be able to choose different number of blocks, which we shall talk about this later. So this is the circuit for our non-abelian Grover search. This is a U sub T is query to the oracle. This is reflection in S, a diffusion operator. And then this was global. To the left is normal global Grover algorithm. And to the right, we have local one. So the same query to the oracle, U sub T. And then this local search, which is diffusion operator for a block, not for the whole database. So from theoretical point of view, Grover algorithm, of course, is a unitary operation in a very large dimensional Hilbert space. The dimension of the Hilbert space equal to the n capital number of entries into the database. But actual development of Grover algorithm is in two-dimensional plane, which is spanned by this S, by this T target item and S total average. So this is just element of O2, normal, usual Grover. Our version of search, which we call non-abelian, is three-dimensional. So there is three different basis vectors. So it's not O2 anymore, but it's O3. And then it's kind of more rich structure. By the way, later when we will be able to use different partitions of the database into different blocks, this dimension of the sphere will increase, and we shall have like O5 and O7. So now we have three strategies to reduce noise. Well, first of all, we shall use hybrid search, classical and quantum, meaning that sometimes, since we're using small quantum computers, sometimes we'll be guessing some of the bits which give the address of the target item. And also, we shall optimize the search by wisely using this partial diffusion operator, and then we shall also measure in the middle of running of the algorithm, divide and conquer. Okay, three strategies can be joined together, and then this different. Well, what we're trying to say is that different computers has different connectivity, and in the future there will be more computers with quantum computers with a different connectivity. So the optimal version of the quantum search, this non-abelian, will depend on the specific hardware, on the specific connectivity of the qubits in the computer, and we'll talk about this more later. So, so how we set up? How we set up our algorithm when we run it on the specific computer. We choose the toy oracle with a single, which is a single qubit equivalent to n Toffoli gate. We choose a target item randomly, and then we run 30 trials with these 8,000 shots. Right now, I'm about to show some pictures, the results of, so we run our non-abelian Grover on some small computers, and then there will be some pictures, figures, and this is notations, which will appear in the next frame. So G3 is diffusion in the 3 qubits, and then M3 is a measurement. This G2 is partial search, diffusion on 2 qubits, and G1 is guess 1, diffusion on 2, measurement on 3, and this is just two-stage diffusion, measurement, and then diffusion on the 2 remaining qubits and the measurement of 2. Okay, so let's see, we run this on the small quantum computer with a 3 qubit. 3 qubits. So concentrate, first look to the left on the second column. This is Grover. Grover is D3, D3, M3. This is standard normal Grover from the textbook. So the probability to find it, the diamond to the right, is very, very high. But when I put this through the computer, the result to the left, this is a straight line with a circle, it's very low. And so the difference is noise. The reason is the noise. So the noise is really damaging Grover. And then if I look to the right, I can find the same Grover, and D3, D3, M3. I see that this depth is very large. So the green one is a theoretical depth. The lighter blue is the depth in Vigo. And then it's very, very large. That's the reason of this such a bad damage of the Grover. So let's have a look at the other one, D2 and 1, D2. So theoretically, it's supposed to give lower probability comparing to Grover, but in practice, it's better. it's better. It gives higher probability. And then I look to the right, to the depths, D2 and 1. So the depth is somewhat lower. So let's move to the 4-qubit. 4-qubit, the Grover, the full Grover. The full Grover is the second line to the left. The full Grover, this diamond to the right, is theoretical probability to find target item, which is very, very high. It's really close to 1. On the other hand, what come out of the computer is very low probability. So everything is damaged by noise badly. And then I can look to the right. This Grover is up. So the depth, especially on Vigo, is very, very large. So the depth damaging, that's a noise which damaging Grover. So let's have a look at the other one, the last one, for example, D2, M2. So theoretically, the probability to find is much larger than Grover. But in practice, this is a straight line with a circle, it is larger than Grover. So I look to the right, to the depths, to M2, D2, M2, D2, M2. This shows that the depth is much, much lower than the Grover. Grover was the first one. Our non-abelian is lowest one. So lower depths, less noise. So 5-qubit. 5-qubit, I only have this table, but the table also drastic because the first line is Grover, diffusion in the 5 qubits and measurement of 5, which give probability was relatively high, 25%, more than 25%. Our non-abelian is G3, D2, M2 to the gas, local diffusion and measurement theoretically give lower probability to find 1/2 of the Grover, but in practice it's the other way around. So in practice, in Casablanca, the Grover actually give a correct answer with probability which is about 3%, but our go much larger, it's about 10%. So this also shows that the reduction of the depths will use less 2-qubit gates, and then 2-qubit gates are noisy. So that's our idea. So this is a degraded ratio. It's NISQ devices. So this is a ratio of the probability on the real device divided by the theoretical probability. So, and horizontally, I have number of 2-qubit gates, and vertically this ratio. I mean, it would be good if ratio is equal to 1, but of course it's smaller than 1 because of the noise. So see, when I have a small amount of 2-qubit gates, like below 20, this ratio is 80%, which is not so bad. On the other hand, if the number of 2-qubit gates is larger than 30, then noise damage everything really badly, and this ratio of the real device result to theoretical about 20%. This is like a phase transition in physics, speaking of physics language. So conclusion of our lecture. So Grover algorithm is not optimally in depth. We're reducing the depth, and this reduces noise and improves the results. And the actual, well, we have different versions of our non-abelian version of Grover, which is a different partition of database into different partitions. And also we have this global diffusion and local, they don't commute with one another. So we can choose the different order. And this is the resource which we intend to use to adjust our non-abelian search to specific hardware. So in the future, the new quantum computers will be built, and each of them will need a specific modification of Grover to become more efficient. So that's what more or less it's said. Connectivity of future quantum devices will be complicated. We'll have loops, and then on the different stages of application of our algorithm, which you can use different division of the database into different sizes of the blocks, and then instead of O2 group, which is normal Grover commutative, we will have or M+1 group, where M is number of different diffusion operators. So maybe we discuss O3, but maybe O5 or further, and then which will give us further.
Thanks a lot, Vladimir, but we'll have to jump over to the next speaker since we're already running over time. Thank you very, very much for this great talk. But for the sake of time, we'll have to directly jump to the next speaker. If there are any questions coming up, please type them in. We'll hand them over to Vladimir and try to get back to you. So thanks a lot. Can you maybe stop sharing your screen?
Where is stop share? Do you know? Wait, I'm working on this. Where is stop share? In here.
Wait, I'm trying.
Share. So, yeah, I stop share. I stop share.
Okay, great. Perfect. Okay, so next up is going to speak Pedro Rivero from the Argonne National Laboratory and the Illinois Institute of Technology, and he'll be talking about an optimal quantum sampling regression algorithm for variational eigensolving in the low qubit number regime. So please, Pedro, take it away.
Okay, thank you very much. Can you hear me?
Yes,
okay,
we can.
Perfect. And you can see my slides, right?
Yes, we can see your slides. Great.
Awesome. So thank you very much for having me. Thank you very much for the nice introduction. My name is Pedro Rivero. I'm a PhD candidate at Illinois Institute of Technology, doing research at Argonne National Lab. And today I'm going to be talking to you about a quantum sampling regression algorithm for variational eigensolving in the low qubit number regime. This is you can actually find a manuscript for this work at the archive, and let's get started. So this is a brief summary of what I'll be touching on in this talk. I will start by giving a brief introduction to VQE and motivating kind of why we need to develop this quantum sampling regression algorithm. Then I'll speak about this new algorithm. I'll talk about the algorithmic complexity and compare it with that of VQE in the low qubit number regime. And then I will move on to applications, benchmarking, and conclusions. So first of all, I'm pretty sure that you all have heard about the VQE algorithm. This is probably the most widely known quantum classical algorithm for variational eigensolving. And the way it works is actually pretty straightforward, right? You only have a classical optimization loop, and inside that classical loop, you just embed a quantum processor unit to perform some of the most costly operations, such as evaluating the target function, which might be an energy landscape, for instance. So a typical loop in VQE will work as follows. You start off with an initial set of parameters. You prepare a quantum state in the quantum processor. According to these parameters, you measure certain expectation value function for that state, and then with that result, you actually decide what the next set of parameters is going to be according to certain optimization logic in a classical computer. Now, the issue here comes whenever you need to establish a connection to the quantum processor unit via the internet for every optimization loop, for every loop in the optimization cycle. So this actually introduces a pronounced bottleneck that makes the whole process actually very slow. And it means that for running VQE on actual hardware, you're actually going to need to spend a lot of time just connecting to the internet or waiting for queues. And this is what motivated us to develop our new algorithm. This is what it looks like. And the way it works is actually pretty straightforward. What we do as compared to VQE is, first of all, we decide which samples we need to take from the quantum processor right at the beginning using a classical decider. Then we query the quantum processor just in one go or very few number of connections, and we retrieve all the evaluations of the expectation value function for all those samples that we requested. And from those, then we'll go on and reconstruct the energy landscape using a trigonometric series. Once we have that function reconstructed, what we do is just perform the optimization in isolation inside the classical processor unit. And this actually allows for a much faster convergence. So what were the insights that actually led us to be able to develop this algorithm? First of all, we noticed that we had, in the parameterization ancestors, we actually had rotations implemented in our quantum circuits. That led us to actually realize that the domain in the function that we wanted to optimize was going to be bounded and periodic. And that pointed us to using a trigonometric series expansion. But this wasn't enough. We also needed to realize that by analyzing the topology of this quantum circuit, implementing the different quantum states, we could actually find frequency bounds for these functions. And once we knew that, we realized that we could actually use Fourier analysis as the natural theory to study what the energy landscape was going to look like. So we went on and just reconstruct that target function as a trigonometric series. What you're seeing on screen right now is just the simple 1D case, but just extending it to multiple dimensions is rather straightforward. And so now our problem is just to find these coefficients to kind of have the trigonometric series reconstructed. And that is just as simple as solving a linear system, which, of course, due to our imprecisions in measuring the energy landscape out of the quantum processor directly, that linear system is going to turn out inconsistent. So it's a good thing that we actually normalize it. This is essentially equivalent to performing least square solutions. And once we do that, this is the actual number of samples that we need to take from the quantum processor in order to be able to solve the linear system and reconstruct the function as a truncated trigonometric series. You see that we have actually modeled that total number of samples as 2 to the Sn, where S is just a parameter that talks about or encodes the information of how many samples we need, and N is just the number of parameters in our parameterization ansatz. All right, so the optimality of the QSR algorithm is actually proven by the Nyquist-Shannon sampling theorem, which actually establishes a minimum number of samples that need to be taken from a given function in order to fully reconstruct it. And this essentially says that we need over twice as many, the sampling rate needs to be larger than twice the highest frequency that we have in that function. And this is a nice approach, actually, because now that we are doing this kind of regression function and using frequencies and Fourier analysis, we can actually use all of our signal processing techniques to be able to improve our algorithm, and actually we can make use of, say, compressed sensing to be able to reconstruct the function using even less samples than those required by the Nyquist-Shannon sampling theorem, and still retain a lot of precision in our results. We can also use this for error mitigation. So we can actually think of increasing the amount of samples that we are taking. This will actually give results with much higher fidelity, or just simply change the spacing in the lattice that we're using to get the samples from the energy landscape. So how does this perform compared to VQE? So as many of you may know, VQE is thought to be valuable, especially when we don't have access to a large amount of quantum resources. This is because if we did so, then we could actually perform error correction, and other algorithms such as phase estimation would be available. So we wanted to study what the algorithmic complexity of both VQE and QSR were in the low qubit number regime. And to do that, we came up with this algorithmic complexity model, which is based, first of all, in a lower bound for the VQE complexity, which is assumed to be polynomial. And we actually just used the most general monomial possible, which is of the form mn to the p, to again lower bound the complexity of VQE. And then we just described the complexity of QSR with the number of samples that we actually need to take from the quantum processor, and that's again 2 to the Sn. So with that in mind, this is the resulting complexity model that we have. You have different plots on the right-hand side of the screen. As you can see, we were able to find a region in the low qubit number regime where QSR performs better than VQE. That's because, as you can see, the costs are actually greater than 1. And once we know this, thanks to having this nice analytical formula, we were able to derive some properties of these distributions, such as the number of parameters to which this distribution peaks, and also the condition to actually have this region in our distribution. So we would actually need n star, where n star is the number of parameters where this distribution peaks, to be greater than E for this region to actually exist and to have QSR actually outperform VQE for a certain amount of parameters. What we also find is that there's always going to be a threshold, right? So there's always going to be a certain amount of parameters above which VQE is going to outperform QSR. And depending on the problem that we're trying to solve, we are going to be past that threshold or before it. And this is something that we need to analyze on a case-by-case basis to see if QSR or VQE is the optimal algorithm for solving our problem. Again, we give analytical formulas for this threshold. As you can see, that's what we call A. And for the algorithmic complexity parameters that we have in our model, we actually see that we can get even as high as 100 ansatz parameters, where QSR is still outperforming VQE. And in the same way, we actually have a way to describe the average efficiency gains in that region. As you can see, these are simple analytical formulas. And in this case, the efficiency grows exponentially when you increase the complexity of optimization in VQE. All right, so let me give you a bit of a scale, of a picture of the scale of problems that we're trying to solve and where QSR would be valuable. So for simulation problems, this is typically in the order of 50 parameters, and the frequency, the parameter S, which reflects the maximum frequency, is around 3. This tells us that when the VQE complexity has an exponent larger than 14, QSR is going to be more effective than VQE. On the other hand, for optimization problems, which are around 10 parameters and much higher maximum frequencies, we're going to have that for exponents larger than 11, so P larger than 11, QSR is actually going to perform better. And last but not least, we have what we call non-frontier problems. These are problems which might not be trying to push quantum computing or make it more efficient than classical computation, but just try to be, say, for instance, proof of concepts. So where we're trying to study or analyze how quantum computers work and if they are actually capable of solving certain problems. And in this case, we have that the optimization complexity of VQE just needs to be higher than 7 plus minus 3, depending on where you are, how your problem actually is depicted. This is so far what we have studied, and we're looking forward to actually implementing QSR for the other cases. But let me continue and talk to you about some of the applications of our novel algorithm. So first of all, as I mentioned before, we can use it to increase precision. This can be done by adjusting the spacing lattice that we're using to recover the samples from the energy landscape. We can actually implement a strategy which is essentially oversampling. This is taking more samples than the minimum required by the Nyberg sampling theorem. And this is going to lead us to having better error rates and higher precision in the end. Also, we can perform what we call undersampling. Undersampling is essentially taking less samples than the minimum required by the Nyberg sampling theorem. And I know this might sound weird at first, but let me give you kind of an intuition of why this can actually be done and why it is interesting. First of all, this will, of course, boost performance. This will make QSR perform better. Second of all, it will get rid of local minima. So for instance, we might have high frequency oscillations that actually lead us to having a very, very bad convergence in any optimization scheme that you're trying to implement. And so by undersampling, we'll be getting rid of these short wavelength oscillations, and actually we will be able to implement faster optimization processes. And last but not least, we can actually use signal processing techniques, as I said before, to retain a lot of precision while still making the algorithm perform better. We also have a number of complementary uses. So we can, for instance, use.
Maybe you can wrap it up since we're already running out of time.
Okay. Can you give me 2 minutes?
Sure.
Okay, perfect. So as I was saying, we can actually use QSR as a low resolution startup to VQE. This means essentially running QSR in an undersampling form, so that we can actually use it just to obtain an approximate solution that we can then use as a better initial state to VQE, which would be an alternative to Hartree-Fock techniques. We can also use it as a proxy to transition between simulators and real devices. And we can use it to avoid the exponential matrix formulation of classical computation. A small benchmark problem, we reproduce the deuterium binding energy from a previous paper, and we can actually see that by analyzing the circuit topology here, we actually saw that in the second case, in the case with 2 parameters, the maximum frequency was doubling, and that's exactly what we expected to happen, and these are the results that we obtained. So on the left-hand side of the slide, you can see a triangulation of the energy landscape as extracted directly from the quantum processor. And on the right-hand side, you can actually see the regression function reconstructed using QSR. These are the results that we obtained. And you can actually see that we were able to perform the optimization not only with better error rates, but also with far less samples and even less queries. We just used, for a case of 2 parameters, 1 query as compared to 183 that we needed with VQE. And for those of you who are interested, we did this using the IBM Q or ENSE and 8192 shots. So conclusions, we can actually use QSR as a global approximation technique that gets rid of connection bottlenecks. For complex enough optimization problems, there will be a region in the low qubit number regime where QSR will outperform VQE. Another nice thing about QSR is that it knows all the samples that need to be taken in advance so that we can actually reduce the number of connections. Then QSR behaves well with a larger range of optimizers. This is because it gets rid of the local stochastic behavior in the target function and allows you to use, say, non-derivative free optimizers, which we know are actually very fast. And also, QSR actually enables signal processing techniques to solve optimization problems more efficiently. And last but not least, QSR can be used in conjunction with other algorithms such as VQE. And with that, I will wrap up. Thank you so much for listening today.
Hello, everyone. My name is Travis Schulten. I work as an applications researcher here at IBM Quantum, and I will be your host for this final session of Track 2 today here at QC40. We have 4 speakers in this session. A reminder that each talk will be about 15 minutes, followed by 5 minutes of Q&A. Feel free to post your questions in the Q&A box below, and then I will ask those questions of the speakers. Our first speaker today is Leo, who is a PhD student at Harvard University, who will be telling us about strongly universal Hamiltonian simulators. Leo, take it away.
Thank you, Travis, for the kind introduction. The work that I'll present today is about quantum simulation, which is considered one of the most promising applications of quantum computers. Why, you might ask? Well, as Feynman said at this very conference 40 years ago, nature isn't classical. So if you want a simulation of nature, you better make it quantum mechanical. In our work, we decided to focus on analog quantum simulation. This is a task of reproducing one quantum system, H, by another H tilde, with the hope that H tilde is more easily accessible in the experiment. In 2012, Sirac and Zoller argued that analog quantum simulation can be more robust against errors than digital simulation by circuits, and thus they are more promising to implement on near-term quantum devices. And indeed, there have been remarkable technological progress in analog simulation experiments, which are already being used to solve real problems. For example, some of you may have heard about many-body localization and time crystals. Well, these are originally hypothetical phenomena proposed by some physicists. And there has been a lot of debate in the community whether they are real effects or simply artifacts from finite-sized numerical simulation. But recently, in a series of beautiful experiments, analog simulation in the systems of 50-tribe ions from Chris Monroe's group have provided strong experimental evidence that these effects do exist in the real world. As another example, systems of neutral atoms in rearrangeable optical tweezers have been recently used to probe quantum phase transitions. And in the past year, coherent quantum phase transition has been observed across systems as large as 250 atoms, which is almost an order of magnitude larger than the state-of-the-art digital quantum computer. Furthermore, analog simulators have also been proposed to address problems in chemistry, for example, using fermionic atoms in optical lattices. And there have also been some recent progress using superconductors to simulate vibrational spectra in molecules like ozone and water. But besides experiment, there have also been some nice development in the theory of analog simulation. Specifically, it has been recently found by Qubit Montanaro and Piddock in 2017 that some families of Hamiltonian are universal in the sense that they can simulate all other Hamiltonians. So this means that a system as simple as a 2D square lattice of qubits with tunable Heisenberg-type interaction can simulate something as complex as, say, a long-range interacting many-body localized system, or a complicated molecular Hamiltonian, or even the SYK model with all-to-all interactions, which is believed to model certain aspects of black hole and have application in quantum gravity. So if you can implement these simple universal systems in the experiment, you can, in principle, simulate anything you want. I will remark here that the word simulation is actually defined in a very strong sense. What it means is that if you look at the spectrum of your target Hamiltonian H, they're reproduced as the low energy spectrum of your simulator H tilde with some local encoding, encoding given by some operator V tilde. And for the experts, what this means is that the operator H tilde, when it's restricted to the eigenstates below some cutoff delta, is epsilon close to the encoded H in the operator sense. And we also want the encoding V tilde to be eta close to some tensor product decomposition that acts independently on the original particles. And this is important for preserving the locality of observables. Well, this rigorous universality result is very nice because it shows that we can reproduce all the physics of any quantum system by very simple ones. We also care about the resources required in practice. Well, in the analysis of Qubit and others, they found that if you have a target system that's two-dimensional, for example, on a lattice, you can indeed efficiently simulate them on a 2D universal system. And by efficiency here, what I mean is that it only requires polynomial overhead in the particle number as well as the interaction energy between the particles. On the other hand, if you have a target system that's three-dimensional or worse, all-to-all interacting, their analysis showed that the interaction energy required to simulate them with a 2D system scale exponentially, unfortunately. And we call these systems, which may require exponential resources in some cases, as weakly universal. Now, you may wonder, where does this exponential requirement come from? Well, I'll need to tell you a bit more details about the previous work and shed light on the origin of their inefficiencies. So in these previous results, the mapping of the simulator is done by taking the target Hamiltonian H and then applying a bunch of perturbative gadgets to them. For example, you can take some complicated interaction graph and reduce the graph degree with something called the Ford gadget. And it was found later that you can actually implement this gadget while still fitting on a 2D lattice geometry. Doing so allows you to map the input Hamiltonian H to a 2D spin lattice model, as shown in this work by Qubit and others. And we call these models semi-translation invariant because the interaction operator between every pairs of site looks the same, and only the interaction energy, Jij, varies spatially. But if you have a dense interaction graph, like for example in the SYK model, you will need to apply the degree reduction procedure many times in order to map it to a finite dimensional lattice. So in general, you will need log n number of rounds of application of the gadgets. In each round, you would, for example, you can have the degree of each vertex, and in each round, the interaction energy will blow up polynomially. And that basically means that after log n number of rounds, you end up with an exponential overhead in the interaction energy required. And because of these exponentials, these models were only shown to be weakly universal. Now, in our work, we were happily able to show that there are, in fact, simple Hamiltonians that are strongly universal. And here, by strongly universal, we mean that these systems, in addition to being at least weakly universal, they also only require resources that scale polynomially in the target system size, as well as all the precision parameters. This is in contrast to the exponential scaling required for some target Hamiltonians under weak universality. And more concretely, what we're able to show is that we can take any Hamiltonian. They could be three-dimensional, or interacting, doesn't matter. In fact, that we were able to show this is true for any Hamiltonian that can be efficiently simulated by a circuit, which we define as circuit simulable. And it turns out that we can take them and construct the efficient mapping to the 2D spin lattice models that were mentioned earlier. And more concretely, what this means is that if you can implement, for example, the Heisenberg or XY interaction on a 2D square lattice, you can simulate anything you want, that as long as they can be also simulated by a digital quantum computer. And furthermore, we show that something as simple as a 1D spin chain of 8-dimensional particles is also strongly universal. And here, the nearest neighboring interaction is on a line and enforces transitions between configurations. And that's what allows us to perform the simulation. So what this result has established is that there's actually a complexity equivalence between analog and digital quantum simulation, since we have shown that a quantum system can be efficiently simulated by circuits if and only if it has efficient analog simulation. The broader implication here is that analog quantum simulation is more realistic for more general systems than perhaps previously thought. So for the rest of my talk, I will want to give you a taste of a couple of key ideas in how we constructed our results. The first idea is a method to perform degree reduction of the interaction graph in a non-perturbative way. Remember from earlier that if you do degree reduction with just perturbative gadgets, you will require exponential energy. Another fact that I haven't mentioned yet is that it is actually impossible in general to perform degree reduction if you allowed only bounded interaction energy. And this was shown by some counterexamples in earlier work by us using information theoretical bounds. Nevertheless, we were able to find a way to perform degree reduction with only polynomial interaction energy. And this is done via circuits, which I will explain now. So the idea is to take any target Hamiltonian, which could be OTO interacting, doesn't matter. And here I've written it down as a decomposition into eigenstates, but I actually don't need to know them explicitly. We can then consider the quantum phase estimation circuit running on the unitary e to the IH tau. Now, this phase estimation circuit takes any eigenstate of H as input and writes down its energy eigenvalue as a bit string on some ancilla. Now, in the context of circuits, degree reduction is much easier to achieve than in the Hamiltonian context, since we can use ancilla qubits and swap gates. What I mean is this. Take your circuit with some unitaries acting on pairs of qubits. We want to reduce the degree of each qubit, which in the context of circuits corresponds to how many gates are applied to each qubit. And we can easily do this by adding fresh ancilla after performing each gate and swapping the quantum states of the qubits to the ancilla after the gate. Then in the subsequent computations in the circuit, they're all performed on the new ancillas, whereas the original qubits are never touched again. So as you can see, without much trouble, we have reduced the degree of qubit A and B in this diagram, for example, to a constant. And we can make this construction more sophisticated and create a circuit embeddable in 2 dimensions in a spatially sparse way. And then by applying something called the Kitaev circuit to Hamiltonian mapping, allows us to transform the phase estimation circuit to a 2D Hamiltonian whose ground states encode the circuit computational history. But this trick on its own is not enough. We still need to be able to distinguish the eigenvalues between different eigenstates. This can be done via the following idea. We can make use of the fact that in the phase estimation circuit, the energy is written down as a bit string on the ancilla at one point. Then by adding an energy penalty term to the Hamiltonian bit by bit at the appropriate time, we can recover all the eigenvalue structure. Combining these ideas, and as well as a few additional techniques, we were able to efficiently map any Hamiltonian to a simple 2D or 1D system as long as it has an efficient circuit for e to the IH tau. Now, let us compare our results to previous results in the following table. After the initial weak universality result by Qubit and others, there has also been a few other work showing more constructions that have better translational invariance properties. Nonetheless, they all require exponential interaction energy, making them weakly universal, and thus not really practical for implementation. In our work, we were able to construct strongly universal simulators in 2D and 1D, and they only require polynomial resources in both interaction energy and particle number. I want to make a couple remarks here. First, I would note that our results are somewhat tight because, as I mentioned earlier, general simulation with constant interaction energy and constant graph degree is impossible, as we have shown in a previous work. And secondly, I will note that strong universality is actually a strict subset of weak universality. And this is because there are weakly universal families, like these two, that cannot be made strongly universal. And we can actually see this by an information theoretical argument due to the fact that these families of Hamiltonians highlighted here have a very strict form of translational invariance. And because of the fact that this weak universal family cannot be made strongly universal, indeed, strong and weak universality are distinct notions. I will now conclude my talk by summarizing our contributions. We have established that strongly universal analog quantum simulation is possible. In fact, they're possible for any Hamiltonian that one can digitally simulate with circuits. And we have explicitly constructed simple 1D and 2D universal systems with polynomial overhead. And we believe that our result is somewhat tight due to an earlier no-go result. And the takeaway message here is really that analog quantum simulation is more relevant than previously thought for many more systems. I will also list some open questions that we want to address in the future. Firstly, we're interested in whether we can improve the translation invariance properties of our construction and potentially extend them to fermion-based simulators, which might be more suited for simulation of chemistry and quantum field theories. Furthermore, in our work, we did not really use the most efficient construction, and we chose methods that are most straightforward for provable results. So there's actually a lot of improvement, room for improvement, to bring the overhead down to experimentally relevant regimes. And lastly, we want to develop a better theory of noise in these analog quantum simulators, since much of our current understanding is based on heuristics and folklore. In conclusion, I hope I have convinced you that the future of analog quantum simulation is very bright, and I invite all of you to work with us on these questions and beyond. And now I am happy to take any questions.
Wonderful. Thank you so very much for that talk, Leo. I noticed a few questions came in from the audience. One from Raphael asks, what are the general properties that a Hamiltonian must satisfy in order to be considered as universal? Is there any other physical Hamiltonian that is used like spin Hamiltonians?
So I think that perhaps universality is more common than one might think. In fact, that in our work, which is based on a few other results done by Qubit and others, if you consider only, for example, 2D lattice models, most of the, if you consider the space of two-body interactions, most of those two-body interactions will allow you to produce a universal system, in fact, a strongly universal system. But there are definitely constraints because, for example, if you have a fully translationally invariant system, which means that the only free parameter of the model is just the number of particles, in which case they cannot be made strongly universal, which I kind of alluded earlier, because these systems are only described by log n number of bits, because the only free parameter is just the number n. Of the number of particles. So they cannot really be, strongly universal, because in order to describe general systems that you want to simulate, which is given by poly n bit description, you will need a system size at least exponentially large.
Gotcha. Thank you for that answer. There's another question which relates more to sort of fault tolerance and analog simulation. And specifically, it asks, has there been any progress on doing fault tolerance for analog quantum simulation?
I have to say that that is definitely, we do not really know enough about this. And I alluded to this in the last open question that I mentioned. There really isn't any, rigorous theory about fault tolerance in the context of analog simulation. There have been some preliminary steps taken. For example, in the work by Qubit and others, they show that if you assume certain, under certain reasonable physical assumptions about the noise model, you can show that the effective noise, in the actual system correspond to also some kind of local noise in the virtual target system. So in some sense that, perhaps that's actually good enough, because in any realistic system that you want to simulate, there's always going to be noise. So perhaps what you're really doing by implementing the analog simulation is just, implementing the ideal system, but at some effective temperature. But it's not really clear if there's a way to systematically bring this effective temperature down, arbitrarily down. And I think that would be some form of fault tolerance theorem that we would need. But I don't think that there's enough theoretical understanding on this front at all.
Okay, well, that also makes a lot of sense. And then I had one question. I think that'll be the last question for this talk. It sort of concerns, can you help me understand the relationship between the amount of error that you incur in one of these analog quantum simulations and the amount of error that you would incur if you did the corresponding circuit-based simulation? Like, are there practical considerations for which those two errors might actually differ, or the amount of error incurred would be different?
Well, I think that, I think to answer that question, you really need to, be careful about really the form of the noise. Okay. I think that, I work with experimentalists, and I think that, depending on the form of noise, if you kind of change how your protocol is done, it can significantly impact the actual effect on the observables that you care about. So in analog simulation, if you can do it in a way that the noise is sort of is local and then the local observables will also only degrade by a small amount. But potentially, if you consider now running basically a circuit-based simulation on the same system, then maybe there's actually a way to transform the effect of, because in principle you can maybe think about the circuit, which is like a time-dependent Hamiltonian, really, as some kind of another form of analog simulation, but just with a time-dependent Hamiltonian, and maybe there's a way to understand the noise, in the circuit, just like how you would do it in the analog case. But then if you take the circuit and do a bunch of error correction or some kind of mapping with encoding and swap gates, and then I think that then the errors that was local in the analog simulation could become very long local, and I think that this is a situation where analog simulation is potentially more robust because it doesn't require that kind of high level of control. And I think that in order to really answer that question, you need to be really careful about how the simulation is done and what is exactly the form of noise. That
is very sensible. So thank you very much for your talk, Leo. We are going to proceed to the next speaker, who will be Mehdi, and he's going to be, he's a PhD student at MIT, and he's going to have a video presentation about properties of interacting quantum systems with algorithmic applications. So.
All right, thanks for coming to my talk. In this talk, I'll tell you about two problems in the interface of physics and computer science, where the computational perspective, here coming from approximation algorithms and machine learning, gives us insight about the physics of interacting quantum systems. And these insights, in turn, allow us to devise more efficient algorithms for simulating and learning this. All right, thanks for coming to my talk. In this talk, I'll tell you about two problems in the interface of physics and computer science, where the computational perspective, here coming from approximation algorithms and machine learning, gives us insight about the physics of interacting quantum systems. And these insights in turn allow us to devise more efficient algorithms for simulating and learning these systems. So let's get started with the first part. Suppose we have a bunch of quantum particles that you can think of them as quantum spins or qubits that interact with each other. And a reasonable assumption that we're going to make is that the interactions are local and particles only interact with other close by neighbors. The system is kept at some fixed temperature and it's in the equilibrium. We'll mostly work with the inverse of the temperature denoted by beta. We can describe the interactions by what's known as a local. All right, thanks for coming to my talk. In this talk, I'll tell you about two problems in the interface of physics and computer science, where the computational perspective, here coming from approximation algorithms and machine learning, gives us insight about the physics of interacting quantum systems. And these insights in turn allow us to devise more efficient algorithms for simulating and learning these systems. So let's get started with the first part. Suppose we have a bunch of quantum particles that you can think of them as quantum spins or qubits that interact with each other. And a reasonable assumption that we're going to make is that the interactions are local and particles only interact with other close by neighbors. The system is kept at some fixed temperature and it's in the equilibrium. We'll mostly work with the inverse of the temperature denoted by beta. We can describe the interactions by what's known as a local Hamiltonian, where we assign a Hermitian operator to each interaction, here represented by these edges. And we know from quantum mechanics that the eigenvalues and eigenvectors of this Hamiltonian operator are the energy states of this many-body quantum system. In particular, at some fixed temperature, the state of the system is a probabilistic mixture of different energy eigenstates. So in the thermal distribution, the system has energy Ek with a probability proportional to the exponential of minus the inverse temperature times the energy Ek. The normalization factor we get in this probability distribution, which is the sum of these exponential coefficients, is known as the partition function. So it turns out the partition function is not only a normalization factor, but also encodes many useful quantities that we'd like to know about the system, things like the free energy, entropy, average energy, and so on. So in physics and chemistry, we're interested in computing these properties, which typically means finding the partition function. But since these particles live in an exponentially large Hilbert space, exactly evaluating these quantities is intractable. And what we instead want is a reasonable estimate of them. And for us in this talk, this means an epsilon additive approximation to the log of the partition function. Because partition function can be exponentially large, it's often easier to think about estimating its log. So the question is when we can hope for an efficient approximation algorithm for this problem. It turns out the answer depends crucially on the temperature of the system, and there is a very nice connection to the underlying physics of the system. To roughly see this, we can look at the extreme cases first of very high and very low temperatures. At very high temperatures, the system is in the maximally mixed state, and finding the partition function is trivial. It's just the dimension of the system. At very low temperatures, we'll basically evaluate the ground state energy of the system, which is expected to be intractable for both classical and quantum computers. So as you see, there is a transition in the computational hardness. We go from trivial to intractable as we lower the temperature. But in physics, we know about another transition that occurs as we go from high to low temperatures, which is the transition in the phase of the system, or the thermal phase transition. So similar to a magnetic material going from the paramagnetic phase to the ferromagnetic phase, for general interacting quantum systems, we can have a sharp transition between the ordered and the disordered phase, or the high temperature phase and the low temperature phase. And this happens at some critical temperature. There are different ways to characterize these phases. One is using the decay of correlations between particles. So in the disordered phase, two distant observables have exponentially small correlations, given by this covariance form on the left. Whereas in the ordered phase, we may have long-range correlations between distant particles. Another qualitatively different way of thinking about these phases is by using the complex zeros of the partition function. So at real temperatures, the partition function, which is some of these exponential factors, is always a strictly positive number. But If we look at complex temperatures, the partition function can be 0. If we track the location of these zeros as the number of particles in the system increases, it turns out that some of them might approach the real axis and accumulate around a critical point. At this point, the partition function vanishes, and the log of it becomes singular. And this singularity is what we see as a sharp change in the properties of the system. So we call the region before this, where there are no zeros close to the real temperatures, the zero-free region. And this corresponds to the high temperature phase of the system. So as you see, there are these two seemingly different ways of thinking about thermal phase transition, the correlation decay and complex zeros. So one question is whether these actually describe the same phenomenon. Another question is whether there is a connection between these notions of thermal phase transition and the computational hardness of estimating the properties of the system. So it turns out that, at least for classical spin systems, all of these are actually closely connected to each other. There is a very fruitful line of research in computer science that studies these connections. And it's been shown that in the high temperature phase, there are provably efficient algorithms. But after the phase transition point, in the worst case, it's NP hard or intractable to estimate the partition function. So the thermal phase transition can be accompanied by a computational phase transition in this sense. The same question is still not very well understood in the quantum case. And in a joint work I've had with Aram Haru and Saeed Mehraban, we make progress on this. So let me briefly tell you about our results. Our first result uses the characterization of phase transition in terms of complex zeros to show that there is a quasi-polynomial time algorithm to estimate the quantum partition functions in the high temperature phase. So subsequent work has improved this to polynomial time algorithm too. And this is based on a method due to Barvinuk, who's applied this to classical spin systems and other combinatorial problems. And the idea is that at high temperatures, where we're in this zero-free region, the log of the partition function is an analytic function, and therefore its Taylor expansion converges exponentially. So we can start from the infinite temperature and compute the coefficients of the Taylor expansion and use it to evaluate the partition function at some finite temperature. And it turns out that we can do this efficiently. So the algorithm itself is simple, but the challenging task is to determine the extent of the zero-free region, or where the phase transition occurs for a given many-body system. That's the range where our algorithm is guaranteed to work. In our second result, we give a general lower bound on this critical inverse temperature, and we show that there is a disk of constant radius without any zeros inside it. This beta zero corresponds only to the geometric properties of the interactions, like the locality and the norm of the Hamiltonian. So as I mentioned, there is a different characterization of the disordered phase using the correlation decay, which seemingly doesn't have anything to do with complex temperatures. But it's known classically that the range of temperatures where correlations decay exponentially is actually equivalent to the zero-free region. This is a result of Dobrosin and Schlossman. In our work, we show one direction of this equivalence for quantum systems, meaning in the zero-free region, the correlations also decay exponentially. We show this for observables that are at least logarithmically far from each other, but this condition can be removed for commuting Hamiltonians or on a 1D chain. All right, so in summary, I told you about an interesting connection between the thermal phase transition and the computational hardness of estimating the properties of quantum systems. And this is a very good example of an area that the progress in algorithmic methods has helped resolving questions in statistical physics and vice versa. All right, now let me move on to the second part of the talk, which is about a problem in the interface of machine learning and quantum many-body physics. So getting back to this interacting quantum system we had, the problem that I'll discuss next is learning the interactions between particles from local measurements that are done at some fixed known temperature. So we perform some local measurements like these, and we want to use the outcome of these measurements to learn the interactions. One reason we care about this problem is in the context of many-body physics, where we'd like to have methods for testing our theories and models about how quantum particles interact with each other. Another more practical motivation for this tomography problem is in the context of the verification of quantum devices. So many quantum algorithms rely on preparing and sampling from the thermal distribution of a specific Hamiltonian, which is used for optimization and simulation. And we want schemes for verifying that a quantum device is actually preparing the right Hamiltonian and interactions. And at first sight, this might seem like an easy task, and maybe we can just measure some observables on two particles and directly read their interactions from that. But there is a big problem here. If we measure a local observable, all other interactions from across the system can contribute in the thermal average that we read in our measurement. So if we're actually not careful, some back-of-the-envelope calculations might suggest that we need an exponential precision in our local measurements to learn anything about the interactions in the system, which isn't scalable at all, of course. But as I'll show you next, a very similar situation happens in machine learning problems. And there are ways we can actually solve the problem without requiring exponentially many measurements. A very popular model in machine learning and statistics is called the Ising model, or Boltzmann machine, where we have binary random variables on the vertices of a graph. And these variables have a joint probability distribution that looks like this. And this is something also very familiar in physics. It's just the thermal or the Gibbs distribution of a collection of classical spins. Because of the widespread applications of this model and its variants, it's been studied a lot, and we have efficient algorithms for learning it from data. And by learning them, I mean learning these parameters A sub KL that fully specify the distribution. These learning algorithms have an efficient running time, and they also use efficient number of samples. So you might have noticed that this problem is very similar to the quantum learning problem we want to solve. Here, all the quantum stuff is basically replaced by their classical analogs. And it seems the same issue we had before should appear here too. Local measurements are influenced by all other variables or spins, and we can have a ton of correlations present. It turns out that this collection of classical spins have a non-trivial property called the Markov property that lets you get around this issue. So to see what this property is, let's divide these variables into three sets A, B, and C, such that the variables in set A are disconnected from those in C, meaning there is no direct edge between A and C. And all the connection is through set B. Then the Markov property says, conditioned on the variables in the middle set B, there is no further correlation left between variables in set A and C. In other words, all the correlations between A and C is mediated through neighboring variables in B. This means we can nicely factorize the overall distribution into this conditional form, and we can combine this property with another ingredient to get learning algorithms for Ising models or Boltzmann machines. This extra ingredient is called the maximum entropy principle, something that, again, both appears in physics and also in statistics and machine learning. I'll skip the details here. You can ask me about it later. But the point is that this way we can get a sample-efficient learning algorithm, and with more work, also a time-efficient algorithm. So to recap, the classical version of our problem, as you see, occurs naturally in machine learning, and it can be efficiently solved using techniques from this field. Now let's go back to the quantum setting and see how much of this carries over. So it turns out that Markov property that I talked about before doesn't hold in its exact form in quantum systems, meaning we can have very simple systems of, say, 3 particles that are at thermal equilibrium, but the correlation between particles A and C can't be completely removed by conditioning on B. So quantum interactions are inherently different from classical ones in this sense. This kind of complicates the plan of carrying machine learning techniques over to learn quantum interactions. And in a joint work I've had, we show that although this Markov property doesn't hold in quantum systems, there is still another property that quantum many-body systems exhibit that allows us to use the maximum entropy principle and other similar machine learning algorithms to learn from local measurements. So this is a joint work with Anurag Anshu, Srinivasan Arunachalam, and Tomotaga Kawahara. And the property that we established is called the strong convexity of the log partition function, or equivalently the free energy of the system. So this property says that the log partition function provably has this nice convex form as a function of different interaction coefficients. And we can lower bound its second derivatives at each point. So I skipped the proof here, but this property basically ensures that local measurements can be robustly used to learn the interactions in quantum systems. And this gives us a sample efficient algorithm for Hamiltonian learning. Meaning if we have m interactions in the system, it suffices to perform about m cubed over epsilon squared many local measurements on the system to learn them within an error of epsilon. So before our work, the existing results were either heuristic and didn't have performance guarantees, or they needed exponentially many measurements. Okay, so this concludes the second part of the talk. And as you hopefully saw during the talk, there is a nice interplay between the computational aspects and the physics of many-body systems. These were mostly about the finite temperature physics, but we can also use techniques from computer science to study the low temperature properties of these systems. I don't have time to cover this, but in another joint work with Anurag Anshu and Aram Haru, we used tools from communication complexity and quantum algorithms to theoretically establish a new universal feature of gapped ground states. So I invite you to look at our paper if you are interested in finding out more about this. And with that, I thank you for your attention.
Great. So thank you very much, Mehdi, for that talk. I think there was one question which came in from the audience. It was from Arif, who asks, can you use duality transformations and map the NP ordered phase to the tractable disordered phase in the dual system?
I guess the short answer is no, because otherwise you can find efficient algorithms for a problem that we know it's NP hard. All right, thanks for coming to my talk. In this talk, I'll tell you about two problems in the interface of physics and computer science, where the computational perspective, here coming from approximation algorithms and machine learning, gives us insight about the physics of interacting quantum systems. And these insights, in turn, allow us to...
Okay, sorry about that, folks. Mehdi, would you like to resume the answer to the question? Would you like me to repeat the question?
Yeah, so it's unlikely to have such reductions between the ordered and the disordered phase, because we know that the ordered phase is NP hard. And this suggests that the duality that the person who asked the question is referring to breaks for the many-body systems that we have this computational hardness for.
Okay. Now, your work kind of glued together two interrelated ideas, sort of some ideas from classical machine learning and then some things about interacting quantum systems. What are some of the interesting open questions that you would like to tackle, kind of presumably over the course of the rest of your PhD?
I guess one question that is related to the second part of the talk is that the learning algorithms that I presented has only efficiency in the number of samples, so the number of measurements that you do scales polynomially with the number of particles, but the running time of the algorithm that processes this information could be exponential. And that's because the algorithm basically needs to work with and estimate the partition function of the system that I showed you in the first part of the talk can only be done for a certain range of temperatures. But classically, we know for spin systems, we can have
my talk. In this talk
for
Go ahead, Mehdi.
We can have efficient algorithms even in the ordered phase where simulating the system is hard, but learning it is not. So it would be very nice to recover this in the quantum setting, and that's an open problem that I'd be interested in.
Okay, cool. Thank you again for that talk, Mehdi. That was very informative.
You're very welcome.
Our next speaker, go ahead and I'll advance the slide here. At least try to. This is my first time using this platform. Our next speaker is Saeed, who is a PhD student at the Department of Electrical Engineering over at Princeton University. And he's going to be talking to us, I guess, about machine learning and physical systems and quantum to classical transitions. Saeed, take it away.
Thanks a lot, Travis, for the kind introduction. Are you able to see my slides?
Yes.
Okay, excellent. Thank you. So thanks again, and thank you also to the organizers for what has been an excellent conference. So today I'll be sharing with you some theory work from the Turecci group at Princeton University in collaboration with Michael Hatfidge over at the University of Pittsburgh in using quantum reservoir computing as a computational paradigm in circuit QED. So in recent years, there have been several significant strides towards the development of universal quantum computation in the circuit QED platform, and several of our colleagues continue to work very hard in addressing the challenges posed, for example, chiefly scalability, maintaining coherence times, while maintaining gate fidelities and correcting the errors that inevitably occur during the computation. Now, in the meantime, and aided by these efforts, circuit QED experiments have evolved in scope and complexity and regularly realize multi-mode nonlinear quantum systems, such as multi-mode amplifiers and Josephson junction arrays. Now, this naturally raises the question of whether we can make use of these multi-mode open nonlinear quantum systems for some non-trivial computation in the near term. And in particular, we feel that these quantum devices can be ideally suited as processors within a machine learning framework, in particular, reservoir computing, the emerging field of reservoir computing. So to briefly introduce what reservoir computing is, it is basically a branch of machine learning where the processing of input signals is encoded into the driven dissipative dynamics of a nonlinear system, the so-called reservoir. And apologies for overloading the term reservoir. It was already overloaded in quantum optics. The output JFT from this processing step then passes through a typically linear output layer, which is often implemented in software and also includes these training weights WO, which are the only trainable weights in this framework. Now, these weights are trained based on the inputs U and the outputs J to perform to realize a trained reservoir computer that implements a certain function on the inputs U, certain function F. Now, the function you desire is determined by the task at hand. For example, state classification, speech recognition, or several other computational tasks that reservoir computing has proven very successful for. And the possible values of the possible functions F that can be realized are, however, restricted by factors such as reservoir size, scale of the nonlinearity, and so on. Now, in particular, we believe this realizes a resource-efficient machine learning paradigm that is suited to near-term quantum devices. And this is because there's no internal weights that need to be microscopically fine-tuned, and the only training can be done efficiently in the software output layer. And there's been recent theory interest in the emerging field of quantum reservoir computing, with proposals to use coupled spin systems and even a single multi-level system as a quantum reservoir for time-dependent processing. Now, for our approach to quantum reservoir computing, we want the ability to process not only classical signals, but also signals that are generated by quantum systems in the same environment as the quantum reservoir computer. Secondly, we want to be able to train on the individual measurement records that are accessible in an actual experiment. To do so, we require a stochastic master equation description of the entire measurement chain, which includes a Liouvillean to describe the measured quantum system LS, a Liouvillean to describe the quantum reservoir computer LQRC, a coupling element LC, as well as stochastic measurement superoperators. Now, unfortunately, for such multi-mode nonlinear systems, the SMEs can be prohibitively expensive to simulate. Instead, we use an effective theory that is based on the first and second order moments of the joint system based on a variational approach by Balian and Veneroni. This approach scales only quadratically with the number of modes instead of exponentially, and we have also verified it to be a very good approximation for weakly nonlinear networks. Now, before I proceed to highlight the multi-mode QRC model, it will be interesting to analyze what kind of nonlinear processing one might expect from such a reservoir. To this end, I'll introduce the single node of our proposed QRC, which is given by this single-driven Kerr oscillator with the nonlinearity lambda. And this is, of course, the lowest order approximation of the Josephson nonlinearity that is used to realize such modes in circuit QED. Now, this single Kerr oscillator, for the moment, sees only a coherent drive via a circulator. And the output from such a system under continuous measurement is given by a field quadrature plus measurement noise. Now, if we look at the amplitude of this, if we look at the expectation value of the field amplitude as a function of the drive strength, here written in terms of this nonlinear, dimensionless nonlinear cooperativity CNL, then we see something that looks as follows. So for weak drives, the response follows that of a linear mode given by the dashed black line that I'm highlighting here. But for strong enough driving, the response deviates and becomes nonlinear. And in this regime, information that is encoded into the drive, the quantum reservoir computer will respond nonlinearly to information that is encoded into the drive strand. Now, this kind of response is typical for this kind of nonlinear oscillator in the vicinity of the classical multi-stability, which is shown by the orange region here, and is typically enhanced as you approach the bistability. Now, one final point here is that for regimes where the nonlinearity is very weak compared to the damping rate, so lambda over gamma of 10 to the minus 3 or less, for example, we see that the response of the quantum system, shown by dots, follows that of its classical nonlinear counterpart, shown in dashed orange. Now, this is not always true. So for example, if you increase the nonlinearity while keeping the nonlinear cooperativity fixed, what you find is that the response of the quantum system starts to deviate from the classical response, which is shown by blue here. And this is actually another feature that is specific to nonlinear quantum systems. So first order quantities like the field amplitude can couple to higher order moments of the system and then hence be modified by them. And this effect increases as the nonlinearity of the system increases and you move towards a more quantum regime. So having analyzed some of the nonlinear processing capabilities of a single QRC node, we can sort of introduce our multi-mode QRC model, which I will talk about now, which is basically just a collection of these individual nodes I just introduced. So a collection of current nonlinear oscillators, which are linearly coupled and damped, and written here in the rotating frame of the single drive that is incident on the entire measurement chain and has a drive strength eta. Now, it proves convenient to describe this kind of multi-mode model in terms of a set of hyperparameters. In particular, the average nonlinearity of the network, lambda bar, the damping rate, gamma bar, coupling, G bar, and detuning, delta bar. And these will eventually be used to understand how the performance of the QRC for certain tasks, how the QRC performs for certain tasks. Now, for the choice of task, we wanted to consider near-term, small-scale quantum reservoir computers. So we chose two particularly simple tasks where the physics of the problem will become apparent. So the first task is going to be the classification of coherent states with different amplitudes and phases, such as those you might obtain from a multi-qubit dispersive measurement. And the second is a classification of two general Gaussian states that differ not in their mean values, but in their second-order moments. Right. So now I'll move on to the first task, for which our measured quantum system becomes a single mode of a cavity. When such a cavity is used for dispersive 2-qubit measurement, the 4-state manifold maps onto 4 cavity pointer states, whose amplitude, phase, and time evolution is now governed by the qubit-induced dispersive shift. This can be seen in the information-carrying cavity X quadrature shown here. And the task of our 2-node QRC in this case is to be able to distinguish between these 4 time-dependent evolutions. Now, to be able to couple this information to the QRC, we use a directional phase-sensitive amplifier, which using a QD interaction following the formalism of Mettleman and Blerk. And what this basically does is that it takes the cavity X quadrature and amplifies it and passes it on to the QRC, which then evolves under this input. Now, the output from this measurement chain includes this evolution, but is obscured by measurement noise and is therefore typically filtered to give you these integrated single-shot records in the sort of measured phase space. And now our linear operation, linear output layer that we use, which involves a matrix multiplication by this matrix WO, then amounts to drawing linear decision boundaries in this phase space. So these 2 dashed lines that you see here to separate these 4 states. Now, however, what we find is that if the nonlinearity, if the QRC is completely linear, so that lambda bar is 0, these 4 states fall along this straight line and cannot be linearly separated using this kind of classifier. However, if the nonlinearity is sufficiently strong enough, the evolution of the 4 states takes it into 4 different regions of phase space that are then linearly separable. So now to quantitatively understand the classification performance, we can repeat these simulations for several initializations of the measurement chain and calculate the mean classification accuracy, which is shown here as a function of time. And this is basically characterized by 2 quantities: the maximum classification fidelity, where 1 indicates that all 4 states are accurately classified, and Tmax, which is the time taken to reach this maximum. Now, we can understand a bit more how this classification unfolds as a function of time by looking at the measured, the phase space of integrated outputs, which I will now show here. So for early times, so what we're showing here are 100 integrated measurement records as a function of time. And at early times, basically the 4 states corresponding to the 4 different colors are completely indistinguishable. Now, as time goes on, we first get a separation between 2 pairs of states that have opposite phases. And these are linearly separable. Now, as the amplitude of the states in the cavity increases, the nonlinearity kicks in. And what it basically does is that it takes the high amplitude states and rotates them away from this linear evolution and separating all four states in phase space such that the classification accuracy reaches 1. Now, you'll note also that the high amplitude, the distributions of the high amplitude states appear to be distorted and in fact squeezed. And this is really just the necessary consequence of squeezing that is associated with the quantum current nonlinearity. Now, of course, this kind of classification requires some strength of nonlinearity, which we will now explore by looking at Cmax and Tmax as a function of lambda. So for convenience, I'm going to set all the damping rates to be the same and set the detunings to 0 and just look at the maximum classification accuracy as a function of nonlinearity. And what we see here is that for weak nonlinearities, the classification for performance is at 0.5, and then it increases to 1 as the nonlinearity strength is increased. Now, this vertical dashed line that you see here is a nonlinearity for which the average Kerr shift of a QRC node is on the order of its line width. Now, this is just a heuristic measure of strongly nonlinear operation and clearly coincides with good classification performance. Now, we can also look at Tmax, which is the time taken to reach this maximum performance in the region where the performance is greater than 99%. And we see that there's actually some kind of optimal value of lambda, where the optimal range of nonlinearities, where the QRC responds fastest or more strongly to the input, and therefore the classification happens in the shortest amount of time. Now, there are, of course, several other hyperparameters that one can look at in terms of tuning and improving performance. But I will leave these for later discussion. And I will move on now to the second task, which we had set out, which was the classification of more general Gaussian states. Now, in this case, I'm going to replace our measured quantum system by a general 2-mode amplifier. And this will be constructed by having 2 types of interactions, a degenerate parametric interaction proportional to G1 and a non-degenerate interaction proportional to G2. And by suitable choice of G1s, G2s, and the drive that is incident on this system, we can engineer 2 different quantum states of the amplifier, which have the same mean amplitude, but different second-order moments, as you can see shown in the Wigner function here. Now, the task of the QRC is then to be able to tell these states apart, even though their mean displacement is the same, by essentially calculating their second-order moments. Now, it turns out that even a linear QRC will be driven to 2 different states. It's hard to see in this plot, but will be different to 2 slightly different states under the action of these 2 different amplifier states. However, what we find is that the mean displacement remains the same. Interestingly, when we have a sufficiently nonlinear QRC, what happens is that not only are the 2 states different in terms of their second-order moments, but they pick up a displacement. And this is related to how I discussed earlier, how lower-order moments couple to higher-order moments for a nonlinear quantum system. So now, interestingly, this displacement is not, in fact, dependent on the drive strength, but actually is related to how well the QRC is able to distinguish the second-order moments of these 2 states, and is therefore a much smaller quantity. We can still see it in the integrated measurement records if we average over a certain number of shots, as what is shown here. So the blue and orange correspond to the 2 different amplifier states. And this is the output of the measurement change for those 2 states. By averaging over a certain number of shots ns, we find this displacement. And therefore, we should be able to tell these states apart if our reservoir computer is nonlinear. So I'll now look at the classification performance as a function of the number of shots that we average over. And so we have Cmax as a function of ns, and starting with nonlinearity, which is 0, so for linear quantum reservoir computer. And what we find here is that Cmax basically hovers around 0.5 with some statistical fluctuations. And the distribution in the measured phase space, basically the 2 distributions overlap. And so there's no hope to tell these 2 states apart using these first-order moments. However, if the quantum reservoir computer is nonlinear, then we see a classification that approaches 1 as a function of ns. And if we look at the distribution in phase space, we see that in addition to the 2 distributions being squeezed, they also pick up a displacement, which then allows them to be linearly separable by drawing this linear decision boundary. So in this way, by using this kind of nonlinear quantum reservoir computer, you're able to avoid nonlinear processing of the measurement records, and you just use a completely linear output layer. So that actually brings me to the end of my talk. What we presented here is an efficient numerical framework to study conditional dynamics of weakly nonlinear multimode quantum systems, which we're writing up and hopefully will be in the archive very soon. What is interesting is that our framework has a very well-defined classical limit as the nonlinearity becomes smaller and smaller, and therefore it should allow us to explore isolate and explore the influence of quantum physics for specific computational tasks. In particular, quantum properties such as entanglement within the reservoir, entanglement of a reservoir with the measured system, and so on. So with that, I will conclude and take any questions.
Cool. Thank you very much for this talk. I don't see any questions coming to us from the audience, but if there are some, please go ahead and type those out furiously right now. I did have a couple of questions that I wanted to ask. So one was concerning your coherent state classification task, right? You talked about how by increasing sort of the total drive time, that these coherent state amplitudes would sort of split out and become more and more linearly separable, and that your classification accuracy would tend to 1. What happens if you were to keep increasing that drive time? Would those amplitudes sort of like start to merge back into one another, or what exactly would happen there?
Right. Eventually, so what is interesting about the coherent state classification task that I had set up, and maybe I didn't explain it fully due to the time limit, but we're not just initializing the cavity in a coherent state and then just seeing that making sure the reservoir is able to figure it out. The cavity always starts in the vacuum state. So basically there's the transient physics you're seeing is because the coherent state is still being developed in the cavity, essentially. So eventually what will happen is that if you go to long enough time, the cavity will settle into a steady state. We're assuming that there's no qubit decays, let's say, because we're just setting up a coherent state. So eventually the blobs should just settle into like different regions of phase space and stop evolving, because we're computing the average displacement of those guys, and that will become constant in the long time limit. Yeah.
Gotcha. Good. Thank you to people in the audience. I see a couple of questions have rolled in here. First from Rafael, who asks, how is the classification affected by coupling, damping, and detuning?
Well, thank you. I will have to reshare my screen if you just give me a second, because those are supplementary slides. But, so this will take just a second.
Sure.
So damping is an interesting one. So these are precisely the things we've looked at in here, which is the performance as a function of the coupling between the reservoir nodes as well as the detuning. And so I'll go over this quickly, but basically it turns out that there's an optimal coupling range. And if your coupling between the two reservoir nodes is too weak, then it's basically like you have one reservoir that is reacting really to the signal, and the second guy. So it turns out the second reservoir node is important for the classification. And so if your G is too weak, it will classify, it will just take longer, and therefore the classification accuracy is above 0.5, but hasn't reached 1 in the time we've looked at. And also you can be overcoupled. So here what happens is that the two reservoir nodes are so strongly coupled, they start to have linear dynamics again. And the nonlinearity, which we need for the classification, kind of goes away, and therefore it becomes suboptimal again. So there's some optimal range. Similarly for detuning, this is interesting. So it turns out that you can, if you start in a non-optimal regime, so for example, I took a large coupling value, there's still some tuning that you can do. So you can move of course, this is circuit QED, you have flux tunable Kerr modes, you can move them around, and by moving to either positive or negative detunings, you can again recover optimal performance. And this actually is related to the fact that our signals are time dependent and transient. And you can basically, by moving the mode frequencies back and forth, or to positive or negative frequencies, you make them effectively resonant with the signal that's coming in, and that helps improve the performance again. And lastly, I don't have a damping plot here, because damping, the problem with damping is that you want your reservoir computer to respond at least as fast as the cavity. So certainly if your reservoir is very slow compared to the cavity decay rate kappa, which I haven't plotted here, I've assumed kappa and gamma to be the same. If it's super slow, then obviously you will classify, it will just take very long. So if your gamma is bigger or equal to the cavity lifetime, or the system lifetime that you're trying to respond to or learn from, then that's a good regime to be in. Of course, if your damping is very large, you have to pump harder. So that's a problem with these systems, with any system really.
Cool.
Okay, so
cool. Well, thank you for that clarifying. And then there's one kind of quick last question here from Raul, who says, "This is exactly what I'm interested in. I just graduated from physics. What learning material and masters would you recommend?"
Oh, awesome. Well, that's a lot of pressure, but that's an awesome question. I don't think I should answer it here, but please feel free to reach out, and we should definitely discuss this offline. Happy to help.
Okay, Raul, you heard it straight from Saeed himself. Find his email address, say I asked you this question at this event, give me the answer, all that good stuff.
Yes.
I think that is the final question that we had for you, Saeed. So thank you very much for your talk. And we will advance to the final speaker of today's session, who is Lev, who is a distinguished professor in the engineering science at the Department of Electrical and Computer Engineering at Boston University. And he's going to be talking to us about fundamental physical capabilities and limitations in communication and computing. Professor, take it away.
Thank you very much, Travis. Let me start with that. My presentation today is more of historical nature, I would say. I'm trying to give a brief review of over 60 years of research in the area of finding out, establishing fundamental physical capabilities on one side and limitation on the other side in communication and computing. It all starts in the 50s, actually, when I was really infatuated with information theory, just reading the foundational work by Shannon. At that time, I was getting my education as a physicist. So I put a sort of a very ambitious goal for me to build a bridge between physics and information science. Of course, it was too much for one person, and indeed it was partially established already by the work of the whole generation of researchers, I would say. Right, but at that point, I must tell you that only a few scientists in the world, those very important, I would say, pioneering figures of Rolf Landauer and Dennis Gabor, and of course I should mention Leon Brillouin with his very influential book, Physics and Information Theory, who really had thoughts and ideas in this direction. Most of the physicists and mathematicians at that time, they believed that that physics and information science completely different areas. They even expressed the idea that the use of the word entropy in both of those fields is just an awkward coincidence, nothing more like that. So now, of course, it is obvious for everybody, but it was not clear at that time. Okay, so let's start from the very beginning. The first effort was concentrated on finding out what are the limits of information transmission by different physical agents. And the first investigated was ideal photon channel with one-dimensional, which means that all the vectors have the same direction. Okay, so it was found that the capacity has a meaning of maximum information rate. The capacity is expressed in terms of power of the radiation and of the signal radiation, right? And the temperature of noise. Noise is supposed to be thermal noise, right? This result was important at the time because actually the classical Shannon theory, it came up with a sort of a paradox of getting the capacity to the infinity when the temperature of noise goes to zero. The no noise capacity becomes infinite. But here, of course, it is clear that it is not. Actually, for temperature going to zero, the capacity would be just proportional to square root of the power of the radiation. An interesting expression which can be derived from this, that if you indeed transmit information with the maximum possible rate over this channel, you get the following expression for the minimum energy per unit of information. You see that there are two different terms here, and one is just the classical that would hold on in classical theory also. But the next term is of quantum nature, and it is proportional to the information transmission rate R, right? So the faster you transmit information, the more energy per unit of information you have to spend. Also was kind of a news at that time, you know. Then the next was ideal photon channel three-dimensional. It means with the variety of directions of wave vectors, which may be directed in different over some solid angles, so to speak. The capacity then is proportional to the power through the, roughly speaking, to the power and the power of the radiation to the power 3/4, right here, where P1 is the noise power here, so it's a ratio of power of the signal radiation to the power of noise. And it turns out that if we transmit information with maximum rate, then the maximum information per photon that can be achieved is expressed just by this interesting expression. This is a Riemann delta function of 3, just a number, actually. So it's about 3.599 nets, natural unit of information per photon. In the previous formulas also, the capacity was in natural units, actually, expressed. Okay. Then if we use not photons, but different type of particles, channels, which I call the ideal corpuscle channels, then for non-relativistic case, I give just with the simple formulas without additive noise. You see, for bosons, it is given by this expression, for fermions with that expression. And you see that actually we do not lose much if we use fermions, though, of course, with the fermions, you have this Pauli law that you cannot put two or more fermions in the same quantum state. But actually, we sacrifice only a factor of square root of 2, which is not much, actually, here. But what is about the general case? At some point, von Neumann made a conjecture that if you transmit a unit of information, then you have to dissipate energy, and the minimum energy dissipation is the kT, where K is supposed to be temperature of the environment. That conjecture was fiercely criticized by Rolf Landauer, and he was right. Actually, Landauer was right, because this is not the temperature of the environment. It is not true. This interpretation is not true. I remember there was a very funny, we argued a lot about different matters, and there was a funny episode at one of the conferences. Then I said in my presentation, I said, I agree with Professor Landauer, but I could not finish because Rolf jumped up and said, I disagree. You know, it was such an episode. He was a great, great scientist, really. His contributions are immortal. But what about this problem? In fact, we should change the formulation of the problem. Okay, we should speak about the minimum energy required for a transmission under noisy conditions, and then it turns out that if we have to introduce a certain concept of effective noise temperature. Effective noise temperature is not the temperature in the environment. It is rather characterized as a strength of interaction between non-controlled degrees of freedom, so to speak, noisy degrees of freedom, and control degrees of freedom that we use for transmitting information. And then it turns out that indeed there is a fundamental limit on the minimum energy per unit of information. This is exactly KT as it was conjectured by von Neumann at that time. Okay, now what about the effect of the quantum measurement? We all know that quantum measurement is a reversible process and all that. How does it show up in information transmission? Well, here we introduced a concept which is called the entropy defect of the system. Namely, if you have a set of signal states, there's a density matrices of a signal I that we use with probability P sub I, then the entropy defect is equal to the actually entropy. This is the expression for the entropy of the average density matrix. You see, this is a weighted sum of density matrix of a system, so it's average density matrix. So it is entropy of average density matrix minus the average of the specific entropies of for each of the signals. Okay, this is what is called entropy defect, and it has interesting properties that it's a positive value always, and this it turns into zero only if all of them are identical. If they are different, the entropy defect is not zero. On the other hand, it is smaller than the entropy of the ensemble of signals, right? This is that entropy. And this limit is achieved only if all of the density matrices are orthogonal. Okay. Now, what about actually the information? That was entropy defect. But what is information in the Shannon sense that we can extract from that ensemble of signals if we use these states to transmit information? So we should consider a sort of a quantum measurement, L capital here, right? And we consider the supremum of the information in Shannon sense that we can extract from this ensemble of signals. It is what I believe Chris Fuchs created that term as accessible information. It is used now, okay? So the basic property is the following, that actually there is an inequality. It is the accessible information is only smaller or maybe equal than the entropy defect. Normally it is smaller. The equality holds only if all of them commute. If there are among our signal density matrices are those which are not commute, then we have strict inequality here, right? This is what I call entropy defect principle, and I established that in 1969 for Neumann measurements, right? However, generalized that actually, got a more general result in 73 for all kinds of measurements involving POVM measurements, indirect, what is called indirect quantum measurements. Okay, and actually the meaning of that it expresses the effect of irreversibility of quantum measurement on information transmission. If you use non-orthogonal states, you always lose some part of the information. Okay, so you cannot achieve that entropy defect I0. But it was kind of a conjecture at that moment that if you do not use this signal state separately, but consider them as components of a huge quantum system, you have a long sequence of such signals, and consider a measurement in the tensor product space of all of those signals, then you can approach the limit of I0. And indeed, that result was brilliantly shown by Schumacher and Westmoreland in 1977, and a little bit later by Olev also. Okay, now, what about relationship between von Neumann and POVM measurements? Actually, POVM measurements, as you know, it is just von Neumann measurement, but performed in a larger Hilbert space, right, in the Hilbert space, with the use of Hilbert space of ancilla, so to speak, right? And it's easy to show that in case if we consider finite dimensional Hilbert space, then there are a number of elegant examples showing that indeed by using indirect the von Neumann measurement, you can extract more information than using just von Neumann measurements, right? So there is an inequality here, okay, for finite dimensional Hilbert space. However, there is a very interesting result that in fact, if you consider infinite dimensional, separable infinite dimensional Hilbert space, right? Then for whatever ancilla you have, you use, you cannot exceed that amount of information achieved by direct von Neumann measurements, right? These two limits, actually, they are supremums, right? These two supremums are equal. Okay,
Dr. Levitin, if I may, we're at 15 minutes now. If you could wrap up in the next 5 minutes, that would be greatly appreciated.
Oh, well, yeah, I have like 3 more points here. Okay, sure. Now we come up with the maximum speed of computation. Now it is called the quantum speed limit. There was a sort of inequality. How fast can a system go from one state to an orthogonal state, to the previous one? That's what constitutes an elementary computational step, because if you make a measurement before that time, you wouldn't get a definite result. So that limit was established as long ago as in 1945, sorry. In 1945 by Mandelstam and Tam. And then independently, Anand and Aronov, who were probably not aware of this result, established it in 1990, and a very elegant proof was given by Weidmann in 92. Okay, so you see, here it is, the time of that transition is lower limited by the standard deviation of the answer, so uncertainty of the energy, right? But Norm Margolis and myself, we found out that in fact there is another quantum speed limit, namely this one, which depends on the average energy of the system. This is average energy above the zero level. Okay, so this really was a kind of created an avalanche of papers in that, which uses and somehow reintroduces this limit. Okay. Also, the generalization of that shows that if you consider a sequence of n orthogonal states, then you do not lose too much. You see this, because for n going to infinity, it becomes 1. So instead of h over 4e, you have h Planck's constant divided by 2e, so a factor of 2 only. Okay, not much. Okay, but what was indeed strange that at this point, for over than 10 years, I would say, we had a strange situation where we had two different limits, one with delta E and another with E, and somehow people just mentioned both of them, and it was not clear because sometimes one is better, sometimes other is better. So I told to Tom Toffoli, I said, look, this is a strange situation. We should find the unified bound of that. And indeed, this this bound was found. I believe I missed that. Maybe I don't see that. Where is that? I don't see that page. I must tell you. I don't understand why. Maybe this one. Oh, this one. No. Okay, that one. You see, actually, there is a unified bound, which is true for any ratio between delta E and E. Here is this parameter alpha. My goodness. And what is interesting that actually this limit, the unified one, it is tight, but it cannot. There are no quantum states that you can exactly get this value. You can only consider approaching it with over a sequence of different quantum states. Okay, so and the only case when it is achievable, okay, you have a quantum state that it will give you this bound, is only for in the case when alpha is equal to 1. Then both of them are the same, delta A and D, and it gives that that limit that was mentioned before, h over 4e, and it corresponds to that number, about 6 times 10 to the power 33 operations per second per joule, right? It's such a sort of a new fundamental constant, I would say, right? Here is the plot that shows how it depends on alpha, right? This is here is the alpha, the ratio, right? And this is that minimum time times this, right? So to get you see these two branches, okay? And here is the sequence of quantum states, initial quantum states that can approach this curve, but cannot touch it, so to speak. The only point where you can do it is when this ratio is 1. Okay, this is one thing. Now, the next is the following. When we have a reversible computing, and quantum computing should be reversible by its nature because we have to keep the quantum state coherent, so to speak, then what is thermodynamic cost of that? Of course, the reversible transformation itself does not imply any increase of entropy, but if you have errors and you have correct those errors, then of course you have to pay that price. You have to dissipate some of the energy. And this is what we found, that indeed you have here is just numerical function that depends on the probability of error. It is different for different system, times HR, the R is the rate of computation. Okay, so you see that the dissipation of energy per unit, per one computational step is proportional to R, which means that that the dissipation per unit of time is proportional to the square of the rate, right? Which is purely quantum effect, because in classical universe, so to speak, the dissipation would be proportional to the rate of computation and not to the square of the rate, right? This is one thing. And maybe the last thing that I'm going to say today is about that issue, the equivalence relation between quantum information and work. You remember this classical Gibbs paradox that if you have two gases which are different, however different, they can be negligible small difference, but if they are indeed distinguishable completely, then there is a mixing entropy of that sort, and you can use this entropy increase in order to convert some heat it is connected to the thermostat, all this stuff, all this system, some heat in order to make mechanical work. For example, lifting, it was a classical Gedanken experiment of, moving some, lifting some weights, right? And this work is proportional to the entropy increase in the system. The paradox, of course, is that a very small, really arbitrarily small difference in the properties creates that jump in the amount of entropy or amount of work, right? In fact, it is not so in quantum case, because if you have two states which are not orthogonal, okay, so they are not completely distinguishable. And then indeed, it turns out that the maximum work that we can obtain is proportional to the accessible information, what is called accessible information, in the ensemble of these two gases, which of course smaller than, in general, smaller than the entropy defect. The question is whether you can achieve entropy defect, and in fact you can do it, but only involving some unitary transformation of the initial states, okay? Then you can obtain that, after all. This equivalence relation between information and work, in general, it is still an open problem. It was shown in a number of examples, particularly our last examples where if you have information in only the two particle correlations, so the first order distributions are like in case of equilibrium, and though there is a deviation from equilibrium only to particle informations, you can use it in order to extract work. And it was also shown that in the case of entanglement, you can extract twice as much work as in the case of statistical correlation of non-entangled particles, right? But in general, it still remains open. And I believe that closes my presentation. Thank you very much.
Thank you very much, Dr. Levitin. That was a very wonderful historical overview of some of the contributions that you and others have made to the field. And I think it really helps bring this afternoon session in particular, maybe even the conference itself, to a very nice close. So I would like to thank you and all of the other speakers for making the time to speak with us today. For the attendees, once this webinar has ended, there'll be a couple of different buttons that'll come up on your screen. I believe we have a couple of different networking lounges available where you can talk with some of the people. And the speakers from this session, for example, can go join that networking lounge as well. I think we have some kind of trivia thing. So if your mind is maybe a little bit addled from all the cool stuff you've been hearing about today, maybe you just want to do some trivia. And thank you all for your very kind attention today. And I guess that wraps up this session. Thank you very much.
Thank you a lot, Travis. Yeah, well.